So nice to see a lot of people already here from the beginning. So this is the 9th edition of the International Workshop on Computer Vision in Sports, usually just called CVsports. I want to thank everyone attending, all the authors sending papers. We had 27 submissions this year, accepted 16 of those, with a great variety of different topics, and I really appreciate that. So I just wanted to start with the program for today. So the first session, we will have an invited talk by Claudio Silva from New York University, and we will have 2 oral talks from the papers. After a short coffee break, we will continue again with another invited talk by Alan Svejstrup from the company Jabra, and 2 oral talks. Then we will have a lunch break of 1.5 hours, continue with our 3rd invited talk by Elise Moore from WSC Sports, and the final oral talk from the papers. And then we'll continue with the spotlights for all the posters, 2 minutes per poster. And then we'll go to the poster session, which is in the exhibit hall. When we come back from that, we will see the results and talks from the SoccerNet challenges this year. And after that, we will present the best paper award for sponsored by SportLogic. And I'll come back with a bit more details about that one. Just a few words of practical information. So we are trying to stream all the old presentations on Zoom. Sometimes that gives a little bit of challenge, but I hope they are able to see this online now. So orals, if you haven't already done so, please come and give the presentation to this laptop and maybe test it in one of the breaks before your session. And for the posters, we have poster boards from 124 to 133. I assigned numbers on our website. You can see all the paper titles and which poster board you should set up at. And I need to inform you that there are different poster sessions going on from all the different workshops today. So we need to set up our posters during the session and then take them back down at the end of the session. And then finally, for the best paper award, we have best paper award sponsored by SportLogic again, of 1,000 Canadian dollars. The winner will be decided. It has not been decided yet, so it will be decided by a combination of the review scores and the votes from all the attendees here. So please pay attention to what you find to be the best paper, also taking into account the presentations here today. So we will do it, Jim is in charge of that. We will do it on paper. So everyone here is invited to take a paper and write the beginning of the title of the paper, and then post your vote. All papers can be voted for, both orals and posters. And we will end the voting after the poster session when we get back here for the SoccerNet challenges. And of course, we expect everyone to be fair and do 1 vote per person. Yes. So let me just see. We will move on with the first invited talk. But I'm not sure if we have anyone. The problem with Zoom is that I can't see it on this screen. So I have to end it here to go back to see if we have people in the waiting room or something I need to take care of. Yes. All right. So then I want to introduce the first speaker, who is the first invited speaker, Claudio Silva, Institute Professor at the Computer Science and Engineering, Data Science at New York University. So I just want to pass the word to you.
Thank you. So thanks, everyone. I particularly want to thank the organizers for this chance to talk to this group. And I'm going to try to make this as kind of like interaction as possible. So here's my plan, right? So I'm going to spend the first my talk actually kind of like has two parts. I'll review some work that I did, like how I actually got into this area about 10 years ago. Um, and one of the things that happened is that has actually, as you're gonna see, like this has shaped, totally kind of like shaped the kind of view that I have for kind of like sports analytics, computer vision, you know. Um, and then I will describe research that our group has been doing more recently. And I have a feeling, I mean, I eliminated a bunch of stuff, but I have a feeling that I might have been a little bit too optimistic on time. But here's what I'm gonna do. I'm gonna try to manage my time so that there is at least 5 minutes, maybe a bit more, for us to actually have a discussion, because I think that that's actually what we get out of a workshop. So I might need to skip a few things, but don't, you know, so don't feel bad. And also, like if I'm going through my talk and there's something that you absolutely have to ask, because it's kind of like it's in your mind, I have also no problem being interrupted. You know, it's totally fine. So I want to acknowledge this is work that I've been doing for over 10 years. You can see this list of people there. I would like to highlight my colleague Carlos Dietrich that started this, you know, kind of like this with me over 10 years ago. But then I mean, there's so many people. So, you know, there's a number of PhD students, master students, you know, like all kinds of postdocs that have worked with me on this, and also people from the different companies. Um, this is actually not an extensive list of everyone. And I want to acknowledge, as being in academia, like we always depend on funding to pay for the students. So I want to acknowledge the funding from a number of companies and funding agencies. Okay, so one slide on background, since I imagine that everyone knows. I mean, our media is full of like claims like, oh, you know, this player is better than that. This is, this, there's so much of this so much about sports, right? Is about gut feeling. So even down to, let's say, when people do scouting, right? So I've actually talked to scouts, and then they say that sometimes it's very hard, even for some of the best scouts, to separate what they see on the field in terms of they just think that someone is stronger and faster than another one just because of some external bias, right? So one of the things that actually should be the goal of here is, how can we objectively, right? How can we objectively, using data, create some understanding of what is actually happening? So we have a chance to not only answer things like this, right, or at least add some actual data into this, but also to help people maybe be less prone to injury. Maybe we can make sports more exciting, so we get more kids, we get people to exercise more. So there's like all kinds of really amazing things that we can do as a group that is, we are working in this area. So for the next like 10 minutes or so, I want to actually review a little bit about MLB StatCast. This is how I got into this. This was like 2012. I got invited into meetings at the time it was MLBAM, and they had this idea that they wanted to, as you're going to see, like they wanted to create new metrics that were based on being able to see the game. And I think some of this actually came from the fact that for those of you that are a sports fan, there was this thing called pitch FX. That was the first time that they actually started to understand where the actual pitches, the balls, the speeds of the balls, were coming. And then they were interested to try to understand, okay, so can we extend this for the whole field, right? So that's how I got into this. So for you might have seen some of this. So just to remind you, this was some of the promo videos from the time. Let's see here. I'm just going to pay a little second of this here. Oops. It just played before. This has a little bit of sound. So one of the things I wanted to say is that that was a promo video. Okay, so this was something that was done, if I remember correctly, around 2015. Okay, so the project was well ongoing at that time. We could generate some of those things, but in again, for those that work in entertainment, that's a promo video. Like someone makes that to make it look cool, to promote the all the things around that, right? Regardless, so one of the things that is interesting is that Statcast actually has actually been amazing, influential, right? And I want actually to highlight to you some of the technical components of this, because I actually feel that a lot of these is not public known. I think part of this reason is actually kind of like our fault for not writing papers on it. But you're going to learn some of these things here. One of the things that happened to this project is that eventually, it was very successful commercially. It got an Emmy, right? It got a bunch of prizes. But I also like to think about, like, when I look at this, I think back at 2012 when we started, right? So when one of the things that was kind of interesting when we started, we are trying to understand. So how do we, so people are giving us input of, we think we can acquire players. How can we turn that into something that is meaningful, that we can actually compute? A very early description, and this might actually be maybe one of the few papers that actually described some of the underlying technology. This was from 2014. This was very early on. This was before actually a lot of the new sensors came into play, right? But one of the things that we're trying to do here is that the idea is, how can we actually capture a digital twin of the game, right? And how can we capture that game, that thing, in such a way that we can compute metrics that people can use on the field? And I'll keep going back to this in a sec. So, and if you see, you probably recognize in this image here, this was actually from the video, from the paper, but here's what we were doing here. So we had vendors that would be providing to us the actual measurements of where the players were, okay, where the ball was. They would be maintaining all that hardware, because this is kind of like pretty big. So we didn't want to create that in-house, but we wanted to make sure that this thing was accurate. Okay, so one of the things we did here, and I'll play this video. It's like a 20-second video here. What this is doing is that if you look at, you're going to see these virtual players. This is what is actually being measured by sensors. Okay, and then what we did is that we put some cameras on top of the of the ballpark. This was actually done in Salt River in Arizona. And then by using computer vision, right, we kind of like, this is kind of like an augmented reality setup, right? You're gonna see if the video plays. Okay, you're gonna see here where the hardware in the stadium is thinking that people are, and then where they actually are in terms of, because we are putting the real data. One of the things that came out of this, right, and we were trying to actually understand what the resolution of these sensors were. It was kind of like a very highly non-trivial process. And if I don't have time, I could spend like my whole talk here just today, just talking about how we make these selections, how we test for accuracy here. But I will refrain from this. But I'll be happy to talk to people offline. But that's kind of like how kind of like we started. So in the end, it was selected that we would be using, Karen's Higo tracking system, a modified version of that, and for the players, And then we'll be using TrackMan at the time for the ball, right? And one of the reasons for this originally was that there was this expectation that in order to track the ball, you know, and actually measure this, like at the time it was better to have the radar there. But these systems are fairly complex. Like if you imagine here, you know, the TrackMan. So these videos seem to play really slowly on this here. Sorry. I don't understand why it's not playing, but so if this doesn't play, I'm just going to go forward. So this is just going to show you that this thing had 6 cameras, you know, because it uses binocular vision and all that stuff, right? Okay, but ultimately, what we really wanted to get out of this, right, was things like this. I think. Can you guys see my mouse? Let's see if I can. Oh yeah. We wanted to get things like this. We wanted to have like arm strength, and we wanted to know, you know, things like throw distance, and we wanted to know the speed of the players. Can we, you know, and actually we had a list. So initially we had a list of literally hundreds of things we wanted to compute. And one of the things that happen is, how do you compute them? How reliable they are? You know, which ones of these can you actually use on air, right? And are reliable for people to actually use for stats. So this actually is what consumed a lot of our time. So I'll try to you know, explain to some of this here. So what you guys are looking at there is a tool that we designed to actually kind of like visualize this. But I'm using this just to show you that we actually had very non-trivial data stream. So a lot of people are like, okay, you know, I put some cameras and I just have my, you know, my baseball game, right? But it's not really that, right? Because for instance, when did the windup start, right? When did the ball leave the pitcher? When did the player touch, you know, what was on the base, right? So all these things you don't get from the video, okay, right? You get, and actually what happened in our case was, we are looking at this and all these measurements are faulty, okay? And I'll describe to you really briefly some of the faults, but there is lots of them, right? Okay, and then, you know, but what we actually had to do was to design something that we call the baseball metrics engine. So what this thing did is that it took all these streams, including the stringer stream. So stringer stream is that there is actually someone on the ballpark that is effectively annotating the game. Okay, this player did that, and you know, and what this thing would do. So our code would do, and I'll show you a little bit how this code, you know, started to happen. Is it would actually take the input that it got, and then it would add stuff to it, and it would integrate all these inputs and then generate a clean game file. Okay, so for instance, I think that there's going to be a talk later today about using physics-based you know, model for modeling like how a ball moves. So in our case, what we had the actual measurements, right, that was coming from the radar, but we couldn't completely trust that for several reasons. So what we did is that we actually had our own. We had a physics-based model for the ball. We would do feeding, and this would actually generate a second stream that actually what we did. Is that we would output all these things. So anytime that they would vary by more than a certain amount, we would say like, here, okay, so this thing is not, you know, they don't match, right? So when you see like the ball going and it's gonna hit somebody, right? Or and then the next thing you know is that you say, this player has this ball, right? But then I have the position of the player and I have the position of the ball, and they are 2 meters apart. Something happened there, right? Okay, so you effectively need to figure out like, what do you do about this, right? So in our case, what we did is that we would actually tag all these things, and some of this output. So we the baseball metrics engine would generate like a whole description of all these changes, okay, and in a clean game. Later, I would actually show you a little video of this working. The kind of infrastructure that was built was really awesome. So all of this at the time, you know, was done in real time. This thing had to run within a few seconds of the processing because on the cloud, because it had to be used for broadcast. So you only had like a minute or two to actually produce what the output was. So that was it was kind of like a really fun thing to do. And then it would generate all these metrics, like all those things, like the arm strength, the way that the people would play. I'm not gonna belabor on this too much now, just because it would take a long time. But yeah, so this idea of reconstruction of the game is really important, and I think that you're gonna see as we switch to more recent work. I think that it plays a really important role. One of the things that was very important here was that effectively a lot of this was actually checked by humans, right? So this thing would generate, right? And I will show you later, like there was actually a few different loops when a human would come and would actually kind of like override or would say that this is right versus that is right, right? So you guys can imagine this was pre-deep learning, okay? This was like, 2012 to 2017 here. We didn't have time to integrate all this, and we didn't have the data at the time. But you can imagine that one of the things that this thing did is to generate millions of examples that you can now use for training, okay? So to, some of the things like the optical tracking system, how accurate it was. So one of the problems is that this is actually not the image that the system would see, right? So if you remember, these cameras are fixed in play, and I'll go back to this point later. So everyone was only like a few pixels apart, and what happens that you have people close to you, let's say maybe the pitcher, right? But then you have people far away from you, right? You have an outfielder. An outfielder is just like a couple of pixels out, okay? So the uncertainty on their movement is extremely different, right, from one another. The ball, there was all kinds of stuff, like you would miss measurements in the beginning and the end. Sometimes people would occlude the line of sight of the radar, so you would also miss that. If the ball went too high, you would lose the field of view. You don't know when it's coming back. So there's all kinds of stuff. You can just imagine. In all these cases, actually happen, right? I mean, you're thinking here about several thousand games every year, and you're thinking of literally hundreds and hundreds of pitches happening in each one of those, right? So all these things happen. So what we've actually did was we kind of built a effectively, we kind of like tried to code the semantics of baseball as a set of, and this is, I'm oversimplifying this here, even if it looks very scary and complex, but you had like a game machine, and then this thing is actually trying to match all these things. You soft matching on this. It's trying to understand, from the beginning of the play to the end, what was happening. And so based on all of that, actually, and things like I told you, like, trying to take physics into account, it tried the best it could, right? So this thing called the baseball metrics engine tried the best it could to build a clean version of a game. So it would integrate all this stuff, right? It would take all the inputs from the different vendors and the input from the stringer and the other things. And then it would do this. It would actually generate also a lot of other byproducts. Some of them I'm not going to describe to you, but it would generate, for instance, information saying, oh, an operator should look at this. Okay, an operator should look at this thing here because maybe this is not very close to reality, right? So here, let me play this little video for you. This is just like a minute video, so you guys can kind of like see the feel of this. This was like, you could then explore any play on the whole, on any season, right? You could query for it. I'm sorry. This is, why is this not plain? This is actually important for us to see. I don't know what the, okay, go. So you guys see, like every time you click on one of these, okay, it would actually compute, it would take the raw data, it would compute what happened. And then you can see like you can move. Those are like game events. The blue ones were actually computed game events versus the orange one that actually were either entered by a human or were automatically measured, okay? And then you could check all the different metrics. So you can, you know, and actually this thing had like, I want to see what the ball, what the raw ball path was from the radar, and I want to see the one that we actually computed by using the physics maze modeling. Okay, so all this stuff, right? You can, and you can look at these trails of the players. This was like super fun to play with this. Okay, and one thing that I mean, I actually thought that it was something that maybe should have been made kind of like widely available so that people could play with it, because it's really neat. And we were probably some of the first people, just because we had the data to be able to look at things like positioning. Like if you actually look, even go back to that 2014 paper, you know, like what actually, as the teams started to get access to the data, you guys saw that they started to actually completely different positioning for what actually led to rule changes most recently, right? So, but you know, we had all this stuff, right? So I want to summarize this so that I can actually, you know, go forward. I think that you know this project and there's, and actually it started effectively with, you know, we had kind of like one sample game, and then we developed like this whole infrastructure for the metrics engine. This turned out to be kind of like a much more complex project than I ever envisioned. This was like 500,000 lines of code, right? And one of the reasons that this was actually embedded, I mean, this is working in production, right? Okay, so what happened is that, and I don't have time for this, but we had all these checks for image quality, right? So you might not notice this thing here. This is actually checking for where the ball, where you have, for a while, we had PitchFX and we had StatCast operating at the same time, right? So you could use one for calibrating the other, at least for trying to understand what those things are. So there's so much nuance to this. We would generate, so the error across different ballparks would actually be different, right? We would keep track of that, and then we would you know, would tell the operators this needs recalibration, right? So if the error went more than a certain amount, someone had to go there and actually recalibrate the whole system, right? So there was like so much cool stuff here. And the BME, as it processed data, I would show you later, it would even generate graphics that summarize the plays, so that there's actually then MLBM started using this in Twitter, right? So anyway, so this was 5 years of my life. Okay, it was really cool, and at the same time, it's slightly frustrating in the sense that, and I know that a lot of you are actually practitioners, is you have these deadlines. I need to have, you know, I need to deploy this by you know, 2 weeks from now, and then you're like, yeah, but I there's a better way to do this. I can, you know, maybe we should redesign that. Maybe we should, you know, and to be honest, during this time, I had no time to do any of that, right? So by late 2017, I was like, all right, look, this baby is working. All the code was robust. Carlos Dietrich and I, effectively, both of us were just like, we just wanted to make sure that we are not part of the engineering path anymore, because for a while, imagine I'm a faculty member, right? Okay, and faculty members usually don't spend all their time writing code. Okay, so I was like, okay, so end of 27, kind of like step aside from the actual operation of this. It was also a time where you might remember MLBAM actually spin off into a separate company called BAM that then immediately got bought by Disney, right? So actually most of the engineering team went with Disney at that time. So you start to think about, okay, so what should be a research agenda driven by a lot of the stuff that you kind of like learn, and then you want to come up with cool questions for students to think about, right? Things that hopefully are not super hard, but that they are kind of interesting. So the way that I kind of like looked at this is that there is like this whole area of like the data acquisition component is extremely important here. Then there is all this analytics. You want to have advanced stats. You want to do things like pair comparison. You want to do what if scenarios. You want to be able to do all that kind of stuff. And then another side that is really also important is kind of like the presentation and delivery, right? So there is so much data here that you want to find some way to show it to people in a good way, right? There's also like new platforms coming along. At the time, we actually played with some AR and VR so that you could take a phone and then put it on top of the ballpark, and then effectively you would get a simplified version of the stuff that I showed you, but in real time. We demoed this at my God, it was one of the all-star games. We were demoing this for the league executives there, like the people in the big seats. So let me show you a few things that we've worked on. And again, I want to be mindful here because I'm going to stop in about 10 minutes so that people can ask questions. So in terms of data acquisition, there was a lot of stuff. So, and again, this is not, I just selected a set of projects that are representative of work that we've been doing in our group. So one of these things is called the NYU Lego Tracker. So the idea here is if you look at StatCast, is this, really like very expensive setup. You have very expensive cameras connected by cables that are connected to computers on the back end, servers, all that stuff, right? There is operators, there is more operators, it runs on the cloud, okay? It's a very expensive setup to run. And then we start things like, what if we can just replace this by a bunch of really like dirt cheap, kind of like collection of intelligent cameras. So the idea here was, imagine that you have these cameras, each one of them looks at the world, they coordinate, so they're somehow all coordinated. There's an orchestrator and you can add more of these on demand as they're doing things, right? And so that was the vision, and I'll show you how far this turned out to be much harder than I thought. Okay, so one of the things was there were lots of kind of like somewhat hard-coded things that we were doing in StatCast for computations, or at least things that were very procedural. And again, like by 2017, we were really like in kind of like through deep learning kind of like approach, right? So one of the first things we said was, okay, so we got a few students, and I think Nina Wilderman was a student from Germany that spent 6 months with us, and what she was exploring was, can I turn all of these things into effectively kind of like just deep learning components, right? So you want to get the pose, you want to localize the player, you want to figure out what kind of pitches they are, so things like this, okay? And again, like this was being done in the context. One of the things that actually helped us is because we had video from the actual games, right? And we had output from StatCast, okay, right? So it actually, and this is actually a game changer, right? Because now it's kind of like I mean, everything we are seeing now in terms of AI is like now, effectively you have label data, okay? So this has fundamentally changed how, once you do all that hard work to generate the systems that generate, a certain amount of data, you can actually improve things quite a lot, right? So, and eventually, I mean, she just spent 6 months with us, but she was able to actually come up with a lot of things that in StatCast were done either by human or by manual annotation, right? She was able to get these with reasonable accuracy. So it gave us, I would say that this is not production quality, like this is not something that you want to deploy tomorrow. But for us, this was more like, hey, is this possible, right? Can we move away, right? From having these really big systems to this, right? So the other really big thing was the actual hardware, right? So one of the problems is, if you look, there's really two things going on here. If you look at the whole field, you're wasting a lot of bandwidth, right? I mean, it's just, and then, how do you zoom into people? Then you create this big problems. Like if you put lots of cameras, you increase your cost a lot. You just, you have to synchronize them. Like cables tend to melt under the sun. We actually had that as we were testing things in Texas, right? So it has been pretty hard. So what I'm showing to you, and I'll show you some data in a sec on this. This is version 3 of the Lego tracker. So concurrently with the work on trying to come up with all the AI algorithms to replace things, we started actually building this hardware. And you can see we went through a bunch of different iterations. So all the idea on each one of these units is that the unit has an AI component, has an AI chip inside, right? So an AI computer, right? And so we want all the processing to actually happen on the unit. So there's no like video. The idea here is that video doesn't get sent out to some place, and it's like the unit do that, right? In order to get this, I mean, you guys probably have noticed this has been like 5-6 years ago. It's been hard. So one of the things, we had to build a whole software framework called REAP, a Reconfigurable Environment Intelligent Platform. And this is open source. And we actually use this in baby steps. So this here is our happy sensor. It's so that this has a microphone array. You can use this sensor. Actually, we use these more for urban scenes. Let's give you an example here. One of the things that is very important on this is that it can synchronize all the frames without cables. So if you look here, all these frames here, there's actually 4 different sensors with 2 cameras each. And they're all synchronized. These are on different sides of the street. So you can actually just, that idea of like being able to use them as like Lego blocks. You just can put another one, okay? And if there's overlap, right, then you can do this. All the synchronization is described in the papers, all that. I'm not gonna describe this to you, but this has all kinds of cool implications. So for instance, you can then do 3D pose detection, right? Because you can have the same pose from different locations and they're synchronized. You know that they're synchronized. Also, the sound is very important. So here, okay, so let me quickly tell you what this thing is. It has a wide view camera. This has this is the AI computer here. It uses a mirror to rotate around and actually follow the tracker. So this is the zoomed view. Okay, so it generates a wide view and a zoomed view, and it tracks the player. So I'll show you the implications of this. So this is here on the field. We're being tested. Let me put this here so that you can kind of like see this thing move. Hopefully. Okay, so the videos are not, one of the disadvantages of using shared laptops is this, it probably doesn't have it cached, and then these are really big videos, but I hope it, oh my God. Okay, this video here, maybe I can, it shows the system in place. So you would see like the mirror, it following someone, okay? maybe after the talk, I'll be happy to show it to you. And this here, but I really need this to play. Okay, so what this thing is gonna do, yeah, okay, guys, I apologize. It runs on my laptop, and I think it. What this shows, okay. Why does this not play? Can I, maybe if I come here, maybe if. No. Oh, yeah. Right. So if you look at this, see, there's like the far away one and the close one. Okay. Right. And so actually what the system is doing is that it uses the other stuff to track this. And then it would actually then keep track of where the moving object is, right? The moving person. And then it would acquire that at much higher res. Okay. What does this actually give you? And it's important that I'm able to play this to you, is that if you look at this person's wrist here, you can barely see them. If you on that, and then if you look here, there is actually their wrist is being tracked with a lot of detail. So actually, that's why I include this. So that's the difference. Okay. So you get the sampling rate on the person's movement is just so low, right? On when you're looking at things in wide angle, right? That at some point you just cannot. You're affected having to guess what happened, right? And in hindsight, to be very honest with you, sometimes when we are doing StatCast and we are trying to improve the algorithms, we're like, why does this not, why can't we not compute this, at higher quality? That's why, right? So we are looking at a field here, right? With effectively like 3 sets of cameras, the signal just is not there, okay? Right? And I feel that this is one of the things, in particular for sports like soccer, like baseball, like that you actually have that you have a lot of dynamic range in terms of the measurements. You're going to need to do this. Okay. All right. Okay. I want to show you. This is really quick. So this is something that I have nothing to do with this. This comes from Carlos, but it's actually pretty cool. Carlos joined these guys from Disney Streaming. They developed this really super cool system. It doesn't have these problems because all the cameras are like at fixed size on UFC, right? But they can do kind of like all this kind of like tracking. So it shows the potential for people to really when you have really like high quality precision, right? Okay, so I think I have very little time, and I have a whole bunch of things I want to show. So here's what I'm going to skip right this. Okay. History Tracker was a paper. A bunch of these are papers that are published. So this was a Kai Bass paper from a few years back. It actually, a lot of this is building on the fact that we have a database of games, right? So this thing has been a game changer, right? Having a database. And then the sports stuff is kind of like similar. So Peter, so actually it's kind of interesting. So Jorge, that was the student that did this work in other pieces, and Peter, there's the student that did this work. Both of their PhD theses won the best computer science thesis in engineering, right? So it just shows you like how much innovation you can do in sports, and so it's been really cool, like working with them. Of course, they're brilliant. So I know it's the other side of this, but there's a bunch of these papers. I'm sorry, I don't have time for this. I'd rather actually use the time to allow you to ask questions, I guess, to give you time to ask questions. Yeah, so why don't I stop here? Hopefully this gives you like a glimpse. The other stuff is actually all the analytics, right? So a bunch of actually like things not on the acquisition side, but on analyzing behavior, computing win probabilities, doing what if scenarios, and also kind of like doing work. So this was something that we would generate from StatCast, and then we noticed that this was not enough for people to understand the timing component, and so kind of like we figured out a way to to get the graphics to be more useful for you for people. This was something that maybe you have seen on Twitter because it gets generated and it's there. Anyway, I'll take questions. I mean, unless you guys prefer that I cover one of the other papers in detail. Thanks for the talk. Really interesting stuff. A lot of the stuff that you presented was like from up to 2017, right? The one that I presented, and then there is all the. Actually, if you look at the papers, all of them are actually from 2017 to here, other than that 2014 one. And then there has been like actually, you know, tens of papers on sports from on Google Scholar. You can find that. Yes. And I'm sorry, I did. Yeah. And I mean, a number of them actually have won prizes at major CS conferences. So yeah. I'm interested in specifically like the PME, the baseball metrics engine, and like where it is now. And that is the paper that I haven't written. So I have a draft, right? And you know, it's one of those things, work that you've done, and you're like, I have this draft, and I need to finish it, okay? And then the student is working on the new stuff, okay? And they need help. What do you do? So, but I definitely, you know, if there is enough, I definitely want to get you know, write that, because as a historical account, I think it's important. And then follow-up is then where do you think it will be like in the next 5 to 10 years? I think that one of the issues is, I think a lot of the technology that was done for baseball is pretty general. So it would work for soccer. I mean, actually, some of this I even see in pieces of what Carlos has been doing for UFC, right? So I think that a lot of this framework for maintaining events and having, you know, and it's very similar. So I actually okay, I try to work with students on see, like we had all these metrics that they were, we would have computations on how to compute the metrics, but now we have millions and millions of these measurements. So when I had a student project that the goal was to just try to use a machine learning model to compute the metrics directly, okay, from the data. I would just train a model that would learn. Now it's arm strength. I show you a play and then you give me arm strength, right? As it turned out, it didn't work very well. And the reason is that even with all the scrubbing of the data we've done, there is still a lot of errors. Okay, so one of the problems here is that there's so many outliers on the stuff. So someone has to further describe the annotations, because, you know, and this has been a problem to just using like a pure deep learning approach to that. So I think that really the right way to do this is probably to generate something that has kind of like the notion of what your game is, and generates a lot of synthetic data that looks realistic, right? Okay, and is hopefully, you know, pretty error free or controlled error, so that you can train algorithms for that. Yes.
Thank you so much for sharing. During the game, there are a lot of distractions. For example, the ball may be here, and the ball may be out of the field. How you are going to find out and avoid these errors? Like, for example, the human in the loop as an annotator to find out where exactly the attention zones are, or how you are going to train the CV model to find out where exactly the game is happening, instead of, for example, looking for other parts.
That's a great question. Yeah, we've thought about this. So one of the things, and I didn't present this, is for sports that you already have enough data, that you already did the work that we did for StatCast, for instance, you actually already have, you can cluster the types of plays, and that's actually what History Tracker uses for that. So you can you can do this automatically, effectively, knowing where things are happening, right, and what's important. I have some videos actually that I could show of some of this technology in being used. But then the question here is like all this bootstrapping. I imagine that the main thing here is how do you bootstrap this for every sport. Thank you.
Then we will have the first oral speaker. All right, yeah. So you may either use this one or
No, I think
that's up to you.
It will be fine.
All right, so the first oral paper here we have today is by Hassan Khalati. So this one is about SoccerNet caption. You're going to present more about that.
Well, good morning, everyone. I hope you're well. Have you ever dreamed to do automatic caption generation of your own soccer games? If so, well, this is the right place, the right moment. Indeed, I will present you SoccerNet Caption, the first dataset for dense video captioning in soccer and the associated tasks with it, as well as a baseline for the 2023 challenge. I'm Hassan Khalati, a master's student at École Polytechnique in ULB, and this work has been done in collaboration with Liège and KAUST. But why dense video captioning is interesting in soccer? Well, actually, there are many applications. For sport broadcaster that may want to have automatic method to generate a caption, but also for teams or players that use more and more data in order to improve their performance, or even for yourself. Imagine you are playing soccer with friends. Wouldn't it be incredible to hear your name after scoring an amazing goal? But there is a big issue for this. Commenting soccer is time-consuming and labor-intensive. Furthermore, from an academic perspective, there is no large-scale datasets in video language in sports with very long entry videos. And processing 90 minutes of videos is very, very hard. But first thing first, what is dense video captioning? Well, originally, given a video, we divide it into several activities bounded in time. We then evaluate the generated activities with a ground truth annotation that overlap. But there is a big issue with this framework. Defining rigorously the starting and stopping time anchors is hard, especially in case of soccer videos. Therefore, along with our datasets, we define a new task for 2020 SoccerNet challenge called single anchored dense video captioning. Each of our ground truth is associated with one single timestamp, and we define beforehand a time window tolerance. In single anchored dense video captioning, the goal is to generate a caption with a single timestamp. At the evaluation, we'll also add a time window tolerance for each generated caption, and then we compute a natural language generation metric such as Meteor, Blue4, Rouge, Cider between the overlapping prediction and the ground truth, and take the average among all the games. Of course, when the ground truths are close together, we may have to compute the metric between a generated caption and more than one. As in this example, where we compute Meteor for ground truth A twice with prediction 1 and 2. Here is an example of one of our captions from our datasets. Edison Cavani, Paris Saint-Germain, connects a great pass inside the box and misses a golden opportunity. His low drive is headed for the bottom right corner, but the goalkeeper pulls off a marvelous diving saving and denies. Well, as you can see, our captions are composed of rich contextual information from the game and are composed of several activities, in that case, 3, and specific expression. We are proud to provide more than 700 of content with more than 36,000 of commentaries among 471 games from 6 major European leagues of soccer. In addition to the original commentaries presented earlier, we provide a version where each player and team is associated with a unique identifier, as well as a version where they are each entity is anonymized. Why? Well, maybe some of you knows Lionel Messi or Ronaldo, but Javier Pastore, I hope some of you also, but for instance, Mark Clattenburg, I don't think. Well, most of the current methods for dense video captioning do not allow generate caption with identifying with specific individuals. However, I'm confident that someone in this room will rise to this challenge and tackle these technical issues in the next iteration of our challenge. We provide to our datasets caption that describes fine-grained action, fine-grained activities using soccer-oriented vocabulary such as box, corner, kick, etc. And as you can see, the two most frequent tokens are team and player names. This highlights indeed the needs of future works in dense video captioning with entities. We are also proud to provide the first datasets made up of whole games. As you can see, there aren't a lot of datasets specific to soccer, but none with an entire game. Also, our videos are quite long on the average. In fact, it is the sum of the longest video with respect to the average duration of a video. This is also the first dataset in using the single anchor dense video captioning task. We also provide a baseline to tackle our challenge. So our method is a two-stage approach, the spotting submodel, using a spotting submodel and a captioning submodel. The spotting submodel, we take a chunk of video and generate the temporal anchor. While the captioning submodel will crop around this temporal anchor and generate the caption. Each submodel is composed by a frozen feature encoder that extracts visual features at the frame level. We then aggregate the frame features into a single clip representation, and the spotting head will then generate the temporal anchor from this hidden vector, while the captioning head, made up of LSTM layers, will generate the caption. We conduct several experiments with different variants of NetVLAT pooling method and several encoders, including the Baidu encoder that was used by the winning team during the previous SoccerNet action spotting challenge. When we use Baidu features, we achieve the best results, especially regarding the captioning. This highlights the necessity of using fine-tuned encoders in order to extract rich contextual information for the game. We also conduct several ablation studies, including one regarding the temporal context we give as inputs to the model. Here, the blue dashed line represents the performance of the spotting submodel, while the orange dashed line represents the performance of the captioning submodel. As you can see, the two submodels require different size. Here, in the case, the spotting submodels requires 15 seconds, while the captioning models require 30 or between 30 and 45 seconds. This motivates further research on the efforts on dynamical temporal context for long video understanding. In our if you remember, I told you that our metric use several natural language metrics such as Blueform, Meteor, Rouge, and Cider. And here we use a 30 seconds time tolerance. So in our last experiment, instead of training the spotting and the captioning submodel independently, both submodels share the aggregator, which we achieve better results when we first train on the captioning and then fine-tuning on the spotting. This suggests that we can achieve better performance if we measure those two tasks during the training and fuse the submodel into a single stage approach. Here is an example of our results. So overall, what you can see, the player takes a corner but fails to find any teammates, and the ball is easily cleared out of the danger. We can generate accurate caption with file description that match to the reality. Here is also another example where there wasn't any ground truth, but the model generate a caption that detects a fault. Well, what's next then? You can come this afternoon to know more about the solution of other participants and prepare yourself for the next year challenge. You can find our code and our challenge with the QR code, and don't forget to come grab your SoccerNet t-shirt. Thank you very much.
Have any questions?
The spotting submodel detects just if there is a caption that should be generated or not, and the caption is quite broad. It can be a fault, corner, a goal. Sometimes if there is a replacement, injuries, it's quite large. Yes, we try to give the context and generate a good caption as it would be done by a professional commentator.
So this captioning is supposed to replace commentator. So ideally, how heavy is this captioning? Run in real time? If so, what type of machine do you use?
Well, at the moment, we haven't done on live inference, but our model is still quite simple. It is based on a previous model on the spotting action challenge that can be run on live, where there is still some work to do it properly, but it should be fine.
Do you aim for it to be live, or is it fine to do some post processing offline?
Ideally, there should be still some post processing in order to filter some captions that are generated, but yeah.
So let's say in some post processing unit for that 45 seconds, so is it can be still be with buffering, or the process what is there? Like we need some data in the future to just caption that. So
no, not really, because we process the video by chain independently. So it is not because we need further information. No, there is still a bit delay. There will be at least a bit delay, but not that much.
Let's thank the speaker again. Then we have a second oral presentation. Yes. So this time by William McNally, talking about the flight of the golf ball.
All right. Yeah. Thank you very much for the introduction. Let's get right into it. So I'm here representing Dunlop Sports. I previously University of Waterloo, where I did pose estimation research, but now working at the U.S. headquarters in Huntington Beach, California, where we mainly focus on R&D for the Srixon and Cleveland Golf products. So anybody here is interested in golf, would love to chat with you throughout the day. But let's get back to the paper. So in this paper, we introduce a new physics-based golf ball flight model, wherein we insert a neural network directly into the differential equations governing the motion of the golf ball. And so the neural network is called at each time step in the simulation, and it estimates the instantaneous aerodynamic coefficients. And kind of one of the key novelties, I guess, of this work is that the ball flight simulation was made end-to-end differentiable, which allows us to train the model just using landing position error. So there's a lot of motivation for why you'd want to improve the accuracy of a ball flight model. They're used heavily in launch monitors and golf simulators. Camera-based launch monitors like the GC Quad just capture the initial window of the golf ball flight, and they use a ball flight model to predict the shot result. Radar-based launch monitors like the TrackMan, they capture the full flight of the golf ball, but ball flight models are used there to provide a normalized result that isn't influenced by weather conditions. Ball flight models are used quite a lot in golf club design, at least in my office, where we tune golf club properties to maximize distance and accuracy using impact and ball flight simulations. They're also used in other areas of golf research, including dynamic golfer models and golf ball aerodynamics. All right, so let's jump right into the physics model. This is a pretty standard setup for a ball flight model where we have the state vector, including the linear velocity, angular velocity, and position. We have the time derivative of the state vector, including the linear acceleration, which is just the net force divided by the mass of the golf ball, the angular acceleration, which is the net torque divided by the rotational inertia, and the linear velocity, which was actually already in the state vector. So assuming we have some representation of these forces, we're able to simulate a full flight of a golf ball, just kind of iteratively stepping through it with a discrete time step using Euler's method. And we chose Euler's method, one, because it's easy to vectorize with a constant time step. So that allows us to simulate multiple flights in parallel. And then also, two, that enables us to be able to train the model in batches of simulated flights. So the simulation is kind of set up as a initial value problem where the initial state of the golf ball is measured by the launch monitor. And so again, for the forces, pretty standard setup where we have a drag force which acts in the direction opposing the velocity of the golf ball. The lift force acts in a direction perpendicular to the ball velocity and the spin vectors. Then we have gravity, and so the net force acting on the golf ball is the sum of those three forces. Something that's a little bit more unique to golf is that the spin rate of the golf ball decays over time, and so we also have a spin decay torque, which we model with this spin decay aerodynamic coefficient Cm. So really, when you look at these equations, the only unknowns are these aerodynamic coefficients. And so if we had representations for these, we'd be able to simulate these ball flights. And that's kind of the tricky part, coming up with good representations for these coefficients. Traditionally, what you do is you probably run some wind tunnel testing at different wind velocities and spin rates and fit an empirical model to that data. Or, that's pretty laborious. So if you didn't have time for that, you'd define some parametric models and tune these the parameters of those over a data set of golf shots. So for example, that's the approach that was used in this paper by Ferguson et al, where they modeled these coefficients parametrically based on the spin ratio of the golf ball, where they used a quadratic model for the lift and drag coefficients and a linear model for the spin decay coefficient. The issue with this is just by selecting this model configuration, you're introducing a bias. In other words, you don't know if any set of these parameters will give a good result. And you also don't know if the spin ratio is a good property to form these models around. So you can kind of see where this is probably going. But in this paper, we address this issue by modeling the aerodynamic coefficients using a neural network, where the input to the neural network is the raw golf ball state with the velocity and spin. So in doing it this way, we automatically learn the optimal representation for these coefficients. And really, this is a very simple model. It's as simple as it gets. It's just a 2-layer feed-forward network. We do run the outputs of the network through a sigmoid function, and that's just to constrain the range of the possible values for these coefficients. So how do we train this thing? So as I mentioned, we implement the entire simulation in PyTorch and make it end-to-end differentiable, which allows us to train the neural network, which estimates the instantaneous aerodynamic coefficients, only using the measured launch conditions and landing positions. So for a single training step, we simulate a batch of flights for 10 seconds, which is longer than any regular golf shot would hang in the air. And so using a discrete time step of 0.1 seconds, we're effectively running this neural network recursively 100 times for each training step. And so after we've simulated the flights, we then detect the landing positions of all the simulated shots, and then compute the landing position error and apply that loss back through. And just to show on the right here, the process we use for detecting the landing position. So this is the height of the golf ball through time. You can take the absolute value of that, multiply by -1, and then you can see that the argmax of this data would be what you're looking for, except that sometimes you might end up with the initial state of the golf ball, so you could just cut that off. And then if you take the argmax of this, what's left, you should get the landing position. And kind of one of the key components of this approach is that we cleverly use the differentiable soft argmax to obtain the landing position so that we could train this model end to end. And I'm sure many of you have heard of soft argmax before. I've just included this slide to quickly provide a refresher about how it works. So essentially you scale your data by some arbitrarily large constant so that when you apply a softmax, you get a value of 1 at the peak and 0 everywhere else. If your scaling factor is large enough, that's what should happen. And then if you multiply this element-wise by the indices and take the sum of that, you should get the index of the max value. All right, so the only thing left now is we need a data set of many launch conditions and landing positions. And so for that, we scraped our internal player tests and robot testing and ended up with 90,000 shots of TrackMan data. And we simply held out the last 10% for validation. And here you can see the distributions of the data sets. All right, moving on to the experiments now. So here we're just comparing the base model to 2 kind of alternative modeling approaches. The first is we found that the lift coefficient and the spin decay coefficients had an interaction for generating the lift force. And so we simplified the learning a little bit by allowing the neural network to just predict the lift and drag coefficients. And then we jointly learned this new parameter PM, which is multiplied by the spin ratio to get the spin decay coefficient. And that seemed to help the neural network learn a little bit and improve convergence. Another thing we tried is just to give the neural network a little bit more flexibility. We introduced this new aerodynamic coefficient CQ, which allowed the neural network to vary the dynamic air pressure. You can see that both of these modifications result in improved convergence and better accuracy. Here you can see the landing position error was improved on the validation set, as well as the max height error. Here is just your standard kind of hyperparameter tuning where we explored different architectures, different number of layers and hidden units in the neural network, as well as batch size to come up with an optimal training configuration. And finally, we experimented with adding terms to the loss function. So in addition to the the landing position error, we also experimented with adding a loss term for the max height. And when we did that, unsurprisingly, the max height error improved quite dramatically. But what was a little bit surprising is that when we ran the full training cycle, we found that when you include the max height error, it actually also improved the landing position error. And so although that wasn't the original intent, I guess our hypothesis is that adding this physical prior helped kind of steer the optimization towards a global minimum. And here we're just comparing our model with some baselines. So you can see here our model outperforms that that quadratic baseline that I mentioned earlier, as well as a neural network that predicts the landing position directly based on the launch conditions. Here's just a visual to show the improvement of our model over the physics model baseline that just uses the quadratic model. Overall, we were able to achieve a 28% reduction in the mean landing position error with this AI-based approach. And then just quickly, I'd like to highlight that because the neural network that we're using is so simple and small, there's actually very minimal computational overhead of simulating with our model, where the simulation time for a single shot on a CPU is just 35 milliseconds, which is much faster than real time when you consider that a golf shot flight time ranges from 4 to 8 seconds. So just to summarize some of the key points of this paper, I think we can say that using a neural network to estimate the aerodynamic coefficients eliminates the bias associated with aerodynamic parameterization of the coefficients and also improves the accuracy. And then we also found that the neural network can be trained using ball flight metadata, thanks to making the entire simulation end-to-end differentiable. And then finally, I'd just like to point out that there's no reason why this approach should be limited to golf. I think it could have many other applications in any sports where you're trying to model the trajectory of projectiles. So thank you for listening, and happy to answer any questions. Yep.
I have a question about this drag coefficient estimation. So drag coefficient of a sphere at Reynolds number of about 10 to the 50 have a sudden drop from 0.5 to 0.2 or 0.3. And for golf ball, I don't know the size of golf ball, but it is 2 inch, which is like 5 centimeters, and speeds around 40 miles, I assume 40 to 50 miles, that sudden drop will happen. Can this method capture that as well? Because that is kind of behavior total change.
Yeah, so let me just start by saying I'm not an aerodynamics expert whatsoever, more of a machine learning engineer. That's definitely something that we'd want to look into, see if the model is actually representing these physical aspects accordingly. And I think that's definitely an area for future work that we'd actually look at the coefficients and see if it behaves as we're expecting.
Okay, thank you. So it's not right now, speed is not something that you consider like low speed, high speed. Can I know what is the speed of the golf ball?
Yeah, so the launch speed can range from probably 20 meters per second to 80 meters per second. And then it would slow down over time from there. Yeah, yeah, you're welcome. Yep.
Are you seeing how your model has compared to have you tried it with the GC quad tracking or see how it that ball flight on?
Yeah, no, I haven't directly compared it to launch monitors, mainly just like this published baseline that was out there. I'm under the impression that it's at least as accurate as what's available, given that, I thought the baseline was probably just as accurate as the launch monitors, and we were able to improve upon that by close to 30%. So I imagine it's quite similar to what a GC quad or a TrackMan would predict.
Let's thank the speaker.
Thank you.
Thanks to all the first authors to keep the time so nicely so we can go on break on the exact time. So now it's time to stretch your legs and maybe grab some coffee and snacks downstairs. And so we will continue again at 10:50, so 10 minutes to 11 with the next invited talk.
Never have time.
Hi. Hi, nice to meet you. Yeah, I saw that you just sent another version. I'm going to download that one.
Lucky to check it.
Yes.
This morning
Yeah.
I was like, oh,
Hi, Christian. I will download it. Yeah. Trackman bliver flittigt nævnt, hva'? Okay. No, nice. Ja. Jeg skal også lige snakke med måske lidt senere om paper med Srishti, der blev færdig. Ja, ja. Det gjorde hun. Ja, hun var super overbevisende. Ja, den kommer altid online. Jeg ved ikke, hvor lang tid det går sådan noget. Hvorfor kommer den her ikke fra?
Jeg arbejder faktisk ikke så meget på det. Ja, det var vist den første, der var sådan det her arbejde direkte.
Kopierer lige den her over, så er vi der. Kan vi lige teste, om din kører? Ja, det plejer. Altså alt det her modtaget har virket okay. Jeg ved ikke, det er lige med, om det så starter automatisk, eller hvordan de gør, men ja.
Det er så ærgerligt, at det er de her stationære mikrofoner, og det ikke er klipper.
Ja, ja.
Så man skal stå sådan helt her.
Ja. Ja, for jeg ved ikke, om de andre er sat til. Sådan, den burde være over nu. Du har også i eftermiddag, ikke?
Jo, så det kan
Ja,
man
så du kan komme og teste. Ja, ja. Yes.
Jeg tror faktisk, det fylder omkring 2 gigabyte i alt.
Okay.
Fem.
Kører den direkte derfra, så i stedet for begynder at stå og kopiere.
Det går rimelig hurtigt. Det hvis det er tilbage i 3.0, så tager det vel ikke lang tid at kopiere et halvt minut tid eller sådan noget. Sindssygt mange sites. 45.000.
Ja.
Hey, hello. Hey. Oh yeah, cool.
Do you want to, grab lunch together or coffee later?
Yeah, absolutely. Let's do that. Like, are you guys working on something similar, or just curious about what we built?
Just curious. We our lab is dynamics,
Uh-huh.
stuff like that. Maybe in 3D vision. So yeah, just interesting.
Of course. Yeah, absolutely, we can do that. I don't know, like, do you? I don't know what the standard is at CVPR, but do you guys organize some like get-together meeting lunches or anything with the speakers?
We don't really do it.
Okay, anything special?
Yeah, not anything organized.
Okay, cool. All right. Yeah, let's just grab lunch then after chat.
After the morning session, the lunches, 12 to 1.
Sounds good to me. Let me just copy over this material here and have a check.
Yeah, lunch is provided, but it's in the main exhibit hall.
Yeah, I believe they gave me some tickets for it.
Yeah, you have tickets for it. Yeah.
Awesome.
It's like 8,000 people gathering together.
So you have to be quick or what?
No, but it's a huge place.
Yeah,
I see.
Pretty packed. A lot of people to sit on the ground.
Yeah.
Yeah. So I'm actually, my background is not in computer science or computer vision. I did math for my PhD, and so our conferences are way smaller.
This is also the biggest one for
Okay.
computer vision.
Yeah.
Yeah, when I started my PhD, it was pretty big, but not as big as right now. It's bigger every year.
Ginormous.
10,000 feet.
Cool. All right.
Nice to meet you.
Nice.
Hi, nice to meet you. Hi, I'm Megan.
Yeah, we are PhDs in Stanford, the LDO.
Do you apply it to small applications sometimes? Thank you.
So should I just put it here? The one that says talks.
Yeah. Yeah, we can just cover it after this one.
There's lots of videos. Some of them are quite big because they're like full fights, and I didn't bother actually cropping them. So, and like in multiple formats, I didn't really know it. Okay, we can say that.
I'll be fine.
We're gonna get
Yeah, thank you.
summer water.
Hi. Everything's good. Yeah, before the next session.
Right, you want me to introduce me to people, right?
Yeah, yes.
I'll do that, sure. Space.
So I stop.
Yes, another thing.
Oh, it's Davis.
Yes. Do you have should have been the type of company? I don't think this one. Right.
Yes,
Yeah, sure.
so we actually, yeah, we were trying to do something. I mean, at one point, this was more of sports history tracker. We wanted to
My father was a boxer.
the same-
Oh, really?
The same scene.
What
So,
about level?
I mean, it'd be
Yeah,
cool,
well,
like,
it was 1940.
1940. Okay, yeah, that's before my
A while
time.
ago. He boxed in New York City.
Okay, awesome. Yeah.
Yeah, it was a local sport. International. Well, it was local and international. There are a lot of boxers back then.
Boxing, yeah, used to be even bigger sport than this today. That is true. It used to be something that everybody watched.
Yeah. Well, they watched it, but they also went to it. Because it wasn't broadcast in 1940.
Oh yeah, exactly. Though it's growing again now, unfortunately. It seems the trend is the combat sports are growing. Yeah, so which is good for us.
Which is good for you.
Yeah, exactly.
It's young Lee is here.
Yes, sure, yeah. Yeah. When it comes to, yeah, I need to check yours, but I didn't give it today, but I think everything has been working. It's just about whether it's automatically.
I know.
Features.
We tried.
And everything is going great in Netflix.
Yeah, busy as usual.
Yeah, I was supposed to download.
You can at least get some notion of what the height
Because he was organizing a workshop there, and we were watching. Unfortunately, we didn't come.
He takes the team professionals.
And he is assistant professor.
Really good. I'm going to highlight where this thing is going. So
Canal, Castro.
No.
It's full professor.
Yeah, he's just, the thing is just that he is.
We get a copy.
Yeah, and then only 10% of the English.
symbols.
Yeah, so that's the
We
thing.
didn't have.
Yeah, I'll probably took about him, but
Okay.
yeah, but
We did some-
sometimes nationality can have issues.
Okay. So going to the US.
It is sometimes a problem. Yeah. Even
It
though
doesn't have
he's been living in Denmark for many years.
Yeah,
but
exactly.
He doesn't have the Danish passport yet. Yeah, so that makes sense.
Actually,
I remember when you were.
Yeah, sure.
there's actually like physics.
You lost a laptop at one point. didn't you? It was a phone from Vegas, yeah. Stay in Vegas.
So it doesn't actually work within the PDF. Yeah, but I think it's all right if I just like, go out of full screen and open the videos. Won't that be okay?
You only have the PDF format.
I also have the other format, but it's the open office kind of format. And when I open it here, it seems to not really work out so well.
with the ODP format. Yeah. So, oh, maybe this. Yeah. No, I'm not so familiar with Windows machines. Like, yes. But it also seems to sort of be missing a lot of stuff here. It's not really readable, right? It looks very different, but the memes look the same. Yeah, but this doesn't really work because it's not really readable. So even if the video runs, then the video, okay, wow, yeah. I guess what I have to do is I just like do the PDF, right? And then close it whenever whenever I want to show a video.
Yeah, just drag the videos to that screen.
Yes. To familiarize myself with the. And how do I make this like the large screen thing? I guess not.
It was not. Yeah, control it. Okay. But then we need to. Yeah.
Does like various shortcuts work? Oh, this works. But then I can just open, whatever. That's fine. I got a lot of videos though, so. But let's just check that the videos run. Seems to be running okay. Cool video.
Yeah. Has it been shared like 1 million times?
I think probably like 10 million people seen this video by now. Yeah.
It's really crazy.
It's absolutely nuts. It was copied so many places. We actually shared it ourselves first on other media too, like Instagram and Twitter and whatnot. But because our accounts were entirely new, we had no followers. So it actually went viral from other people's account on Twitter and Instagram, because they would take it and copy it and put it all in there. Yeah, so.
And that's what where I saw you needed it.
From LinkedIn
From
post,
LinkedIn,
yeah. Oh, it's also missing my little. I put a little heart emoji there. It's very unfortunate. Okay, but it seems to be working. The PDF is working, and I can open the videos in here. So I think I'm happy.
Then I'm just gonna duplicate the screen because right now we're running presenter mode.
Okay.
So we will just duplicate the screen and then you run it here, and we will see the same there.
Awesome.
Yeah.
Oh, awesome. Okay. I see. No, that's a good question. Hey, if you just plug It's the best you can do, I would say. It's not like they are. Yeah, we have like the verification for us.
Hvor mange store er I? Som er det bare dig? Eller? Nej, vi er lidt mere, men det startede med at være meget meget. Ja. Nu er vi 6 stykker. Har vi fået et penge. Hvor er det? Vi er sådan lidt spredt over det hele, men vi er incorporated i Danmark. Så lige jeg sidder i Danmark, og Julia sidder i LA, og så sidder jeg i Shenzhen lige nu sammen med 3 andre.
Er det primært til, altså det er kampsportsanalyse,
Ja.
men er det primært til podcast, eller er det statistik, eller?
Det vil også sådan, at det er lidt. Okay. Jeg har faktisk en rimelig god idé om, hvad jeg gerne vil bygge, hvor det giver mening at tjene nogle penge. Til at starte med, så hedder det bare ord, om jeg kan lave en slags AI-version af noget, der hedder CompuBox, som er noget, man bruger nu i boksen. Ser du noget i boksen?
Nej, overhovedet ikke. Jeg er ikke kamp.
Jeg tænker måske, det er lidt der forkerte crowd her, i forhold til at tænke kampsport. Ikke, jeg tror ikke, der var mange af dem, der var også også. Ja. CompuBox er sådan et program, hvor de sidder og kigger. Så der sidder ligesom 2 gutter og kigger på en kamp. Og så når de mener, at der er en, der har slået slag og har ramt det.
Okay, så det er som baseball, det med tagger.
Ja, men det er ikke særlig præcis. For det måler ikke sådan de mest relevante aspekter af slag. Så når du rammer din modstander, så der er mange måder at ramme modstander på. Der er de der sådan små, hvor der er kontakt, men der måske ikke er begge, hvor det skal tages med eller ej. Så det er de der store slag, som lidt på en eller anden måde tæller at få mere af. Og det er ikke noget, man kan kvantificere. Men så siden der, så er vi udvidet vores ambition en lille smule. Så nu vil vi gerne bygge en virksomhed, det der er bio, men til kampsport.
Okay, så til hobby.
Ja, til long tail og
Det betyder trackman. Det bliver tilbudt at købe bio tidligt.
Så ja, det skal jeg sådan noget amatør, det gider de ikke. Ja, vi har fået ekstremt god respons. Vi kan faktisk allerede lave den der form for autoproduktion nu, post-production. Vi har fået vildt god respons på det, vi måske har testet. Så vi kan virkelig se, at der er et marked.
Men det er også en fed approach, også til sådan forældre og sådan noget, som gerne vil følge med i game story og så videre.
Jeg tror faktisk, at markedet er meget større, eller det er meget bedre product market fit med automated content generation til kampsport, end det er i mange af de andre sport, selv i også. Fordi i kampsport, der er folk jo besatte af optagelser kampe, altså folk sidder med beat. Så er det nærmest ikke bare på tripods, ikke? Og samtidig så er der det der aspekt med at måle, hvad sker der.
Det er jeres løsning lidt eller flere kan
jeg har ikke bygget, hvad skal man sige, vores BO-camp for combat sports. Vores post-production, den kan køre med, den er ekstremt generisk, fordi den var oprindeligt
AI Deep Strike var egentlig designet til at kunne fungere på broadcast feed. Fuldstændig arbitrært. Så på den måde, og som skifter vinkel hele tiden, så man skal lave verification. Det var designet til det, så det var faktisk ret nemt at tilføje noget til Deep Strike, så man kunne lave auto-production, hvor du bare kan stille nogle kameraer, som du kan stikke, og så kører bare. Så man kan bruge 1, 2, 3, 4, teknisk set 100 kameraer i auto-production, hvis du vil. Men man kan efter 3-4 kameraer, så er det så tæt nok.
Men det er så post-installation til, hvornår de er fra?
Nej, det er faktisk måske nærmest vores trick, ikke? Fordi efter vores videokamera, så var der virkelig mange kontakter, så var det samme for eksempel Team USA, som vi arbejder med, fortæller os, at de har fået at lave contract med virksomheden til at lave en tilsvarende, som vi har lavet. Og de måtte efter vores nu står vi bare med på post-installation. Så resultaterne så fine ud til at starte med. Men så er det simpelthen, det er sådan bare noget i et eller andet plateau, og så uanset hvor meget data, der bliver spillet på det, når man kommer ind. Så vores trick er måske nok, at netop det, at vi ikke bruger post-installation. Men der var jo også med helt oprindeligt. Hypotese, der startede alene med det var, der kommer en lille problemer med processtillingen, key points og den. Det er så små detaljer, der ligesom fortæller i landet, og slet ikke landet. Så hvis man så har sådan et intermediate stage med key points.
Thanks. Do you want to test if everything is working?
Det kunne måske være problematisk på et tidspunkt. Det er derfor, jeg
I have like more animations, so maybe like a slideshow should be okay.
I hvert fald 5-6 andre startups, som ligesom
To show it. Or do you want to?
Just like you can start the slideshow.
Yeah,
So I
send
can,
it. Yeah.
Okay. Yeah, I think that should be okay.
Thank you.
Thank you so much.
Men performance assist og CVsports har jo kun videomateriale for en del. Så good luck med 3D process, hvis det giver mening i forhold til, hvad vi gerne vil lave. Så ja, så det var en af de gode beslutninger, vi lavede til at starte med. Ikke at gå den vej. Det er også svært, fordi når man ligesom træner sådan en action recognition models, scratch skal træne. Så vi har 3 data injector til det, som vi laver anden bare. Altså det er sådan halvdelen af en højde beholder, ikke? Så sidder bare og annoterer data for 50 timer.
Så alle kampsport er voksne.
Kun trænet til voksne. Men Deep Strike er sådan rimelig generisk, så det kan også tilpasse til andre sportsgrupper. Men lige nu er vi så et lille hold, det giver måske mere mening for os at få monetized voksne først, inden vi begynder at hoppe over til andre sportsgrupper. Men der er godt nok mange, der skal til at sige, så vi skal også have det mere til kickboxing, muay thai, alle de der sportsgrupper. Så ja. Et af vores største issues er næsten, at vi får for mange e-mails, vi skal svare på hele tiden. Fans, ikke? Så det er meget fedt. Ja.
Og så går der demo.
Ja. Hvilke demos har du set på?
Det var med nogle videoer. Bare for at det godt, at bare med stats og nu strike og så videre.
Okay.
Så meget.
Ja, for vi har lagt nogle nye op for nyligt på YouTube, som har fået lidt opmærksomhed også. Hvor vi tager hele kampen, og så laver en slags overlay graphics og lægger på, sådan, når folk som ser den her kamp, kan se løbende, som det ligner i et computerspil.
Ja, det var der på den, jeg så her.
Okay, ja. Så det er en af de nye så. Ja.
Rikke på det ene optag.
Ja, det burde blive optaget og ligge på CVPR-siden bagefter.
Så skal jeg passe på, hvad jeg siger.
Det er kun dem, der har adgang til CVPR registreret, der kan se det, men stadigvæk, så ved man jo aldrig, hvem de så viser det til.
Nej, for man bliver godt nok overrasket, når man kører stats på mange af de her kampe.
Ja.
Are you Danish?
Ja, det er.
Okay. Okay.
Det er en masterstudie, også tricky på det.
Okay, så også for det. Jeg er faktisk også i gang med det.
Det er også godt.
Svejstrup, ja.
Det er 2 år, hvor matematik var.
Yeah, nogenlunde. Jeg er færdiggjort med bachelor i matematik, så jeg er i gang på overbygning. We can get into that stuff. Okay.
Good times. Jabber.
Yes.
Oh, very as nice. In jabber?
Yeah, as in a jabber, exactly.
Yeah.
You got the name right.
Yeah.
I never got to have a coffee.
No.
I got halfway down there. I was talking.
Then you met someone. I can't make it. No. 1.5 hours, we'll go to lunch instead.
The lunch is downstairs someplace.
Yeah, it's downstairs. Did you go for the breakfast?
No, I didn't even know there was a breakfast.
There was a breakfast on some sort of snack.
Yeah, I guess I saw that.
It's in the same. Yeah, like some of these big
Do
groups.
we use the tickets for that as well? Or?
I don't think so.
Only
You
for the
just have to
lunch.
show this.
Okay, cool.
Yeah, only for lunch you need the ticket, but for breakfast and breaks, you don't.
I'm gonna come earlier tomorrow to get myself an extra breakfast. I'm a bit hungry now.
Yeah. I wouldn't call it advice. Today it was like cakes and yeah, if you like oatmeal, then you could get hot oatmeal.
Oh, they had hot porridge, that's good.
Other than that, it was like cakes and a little bit of fruit.
Cakes and porridge and fruit.
But there
That
were many
sounds good to
different
me.
cakes.
Depends on the quality of the porridge and the cakes.
Yeah.
And the fruit.
And the fruit, yes.
The fruit's the local strawberries I think, right now.
Okay.
Yeah.
Apples and bananas.
Oh.
I think this is, yeah, I haven't been to Canada before, but America.
You haven't?
No, it's my first time here. Usually the breakfast in America is a bit more like the sugar and cake compared to Denmark. So when I see the 5 different types of cakes, it's not really what I'm used to eat for breakfast.
What do you use for breakfast? Porridge and oats? Or?
Yeah, oats, but I like it cold.
They rolled oats, not like oatmeal. They rolled oats
Yeah.
that you did raw with
Rolls
milk.
with
Yeah.
milk, cold milk.
I ate granola, which is sort of slightly cooked.
Yeah, okay, yeah.
Granola yogurt.
Yeah, yogurt. I like that too. Yeah.
Yeah.
Yeah, I'm heading back tomorrow. Yeah. Yeah, it's a great trip.
Yeah, it's not something that
No, I have exams now.
Oh, that's right.
Yeah, but that's not the main thing. The main thing is I have a daughter of 1.5 years. Yeah.
Another one already.
Yeah, so, and also because this pregnancy, I have to go to the doctor every second week. They do scans because it's twins, yeah. So I have to go to these regular scans. And they don't want to have any delays. They need to follow the schedule. So I have to do that later this week.
So you fly back tomorrow.
Yeah, I'll find it tomorrow. I'll be home on Wednesday. So,
Fly back to New York.
no, I fly directly to Amsterdam.
Oh, the Amsterdam,
Vancouver,
yeah.
Amsterdam, and then Aalborg from there. Because I live in Aalborg and have direct connection to Amsterdam.
In a train.
No, flight. Aalborg, Amsterdam. So that's nice.
Now, my introduction to Copenhagen was ECCG.
Okay.
Maybe slightly
Before my time.
maybe it's 2000 or something. Yeah. I went to Malmö just to see what Sweden. And I was thinking, yeah, it's pretty nice. I mean, Copenhagen. I didn't get out of it.
Okay, yeah. And is that based on?
And Henrik Christensen.
Yeah. Yeah, now he's in San Diego, right?
It's always hard to tell. I think. No, USC. So it's LA.
Yeah.
Yeah. One of the things we have is automating collection
Hello, everybody. Let's keep our schedule on time as we so nicely did this morning. It's my pleasure to introduce the first invited speaker of the session, and Alan Sveistrup. CVsports. Yes.
It's so hard to try to transliterate that and get it right. Anyway, he's going to be speaking to us today for something that's very interesting, unusual for this group. We had team sports typically. Now we're going to look at combat sports in computer vision, a match made in heaven, and from Chopper.
Exactly. Thank you, Jim. All right. So this talk is going to be not a technical talk. It's going to be more like a talk about my experience starting Jabber from our humble beginnings until now, which is still very humble, but slightly larger. And we started just me. I was a solo founder doing this project. Started about 2 years ago. And then over the course of the journey, more and more people sort of joined in as they saw what I was building and liked it. So combat sports. There's supposed to be a little red heart emoticon there. It got lost in translation, but you get the idea. How many here has any experience with combat sports, like watch it or something like that? Yeah, a few. Anybody ever been in a fight? Somebody stole your spot at a postal session or something. Yeah. So combat sports, a lot of people say it's really the oldest sport that is out there. If you go back to the classical times, the Olympics, boxing existed there in some rudimentary form. A little bit different than we do boxing today. Back then, there was usually no doubt about who the winner was because there was no rounds, there was no judges, there was just two fighters naked with wraps around their hands fighting until one guy yielded or one guy got knocked out. Then you had a referee whose job with a whip was to keep the spectators away. So slightly different than it is today. In terms of deciding who won the fight, if it ended up taking too long, the ref would stop the fight and have each fighter take turns, punching each other with a free shot until somebody yielded or got knocked out. So as you can imagine, this wasn't great for safety. So today things are done quite differently in boxing. There's something called the Queensberry rules of boxing that's about 150 years old, where rounds were introduced, 3 minutes, 1 minute of breaks, padding for the hands, stopped after a certain amount of time, and then you delegate the decision of who won a fight to judges. Typically 3, but in the amateurs and the Olympics, you often use 5 as well. And great for safety, but introduced a lot of other issues to the sport. So combat sports is huge. Boxing and MMA, millions and millions of followers out there, large money involved. Yet they still continue using this method of having a couple of old guys sitting ringside at the end of the fight. You just ask them, so, what do you think? That's basically how it's done. There's a long list of complicated suggestions for how a fight should be judged, but to be perfectly frank, that's just all gibberish. It's really just about the subjective opinion of each judge. Could you imagine basketball was judged that way? At the end of a match, you'd go and ask 3 guys sitting ringside, sitting courtside. Was that courtside? Ask them, so what do you think? Should it go this way or that way? But that's how it's done in combat sports. So about 2 years ago, I was working at this Chinese computer vision company, and I decided I wanted to leave them and build my own thing. I've been a fan of boxing for many, many years, since I was a teenager. And I knew something was missing in boxing. This sweet science, as people calling, is trailing on tech. I saw at that time so many new products was coming out for many different types of sports in terms of analytics and content creation. Nothing was really happening in combat sports, at least at that time. And I wanted to see if I could create something that could potentially help this issue of judging. So boxing now, for the first time, pretty much since the classical Olympics, might not actually be on the program of the Olympics just because of really extensive match fixing being discovered. One thing I did before I actually started building Jabber was I took a fight, picked a random fight off of YouTube. Alexander Devon, Ivan Rekak, he's Ukrainian. And I slowed it down. I watched the fight, and then every time there was an exchange, pause it, go back, go through the exchange in slow motion and take notes. And I do that throughout the fight. And so 2 things I noticed was that the CompuBox numbers that was presented during this fight were wrong. Probably many of you don't know what CompuBox means, but this is the system where it's used now for entertainment, where you get some numbers about who landed how many shots on who. The way you get it is not really related to computers in any way. You got 2 guys sitting ringside, just like the judges, and then they have like a clicker in the hand. So whenever they feel a guy land a shot, a clicker. Those numbers were not very accurate. And the commentators seem to be favoring Alexander Devon. And so as I went through the fight, I realized they're all completely wrong. Especially when you write, when you're watching such a fast sport as boxing, I realized, even after watching so many years, when you pause it or when you watch in slow motion, suddenly things that were blurry when watching in real time becomes very clear. And it's not really, it's quite easy to see who's actually winning the fight. And I saw Ivan was winning the fight, despite what the CompuBox numbers were saying, despite what the commentators were expressing. And so the 6th round came around, and Ivan knocked out Alexander, to the great surprise of the commentators, and maybe also to the surprise of the clickers doing the CompuBox numbers. Not to me though, after watching in slow motion. So I did this for many different fights, and the pattern just repeated itself again and again and again. Sometimes in ways that are somewhat suspicious, and that's why I put this little meme here, but I'll talk about that a little bit later in the talk. So I wanted to build essentially initially just this AI version of CompuBox. So instead of having 2 guys who sit there and click whenever they feel something landed in this sport that's essentially too fast to do that accurately, let's do it with AI, with computer vision. Computer vision has pretty much, at least compared with humans, infinite reaction speed. So it felt like the right way to go there. I wanted to build something that's simple and easy to use. So no special cameras that needed to be placed around the ring, nothing like that. So just work on the stream that everybody else sees. And it should work with just 1 cam or multiple cams, and ideal historic material as well, because there's hundreds of thousands of fights out there, old fights that could be very interesting to look at with this kind of tech, if could be built. So step 1 in my journey here was raising money, which was a little bit tricky as a solo founder, but actually happened fairly quickly. And once I had done that, I started experimenting a little bit, because I needed then to actually figure out how to build this thing. And I did have some experience here after 2 years working for that Chinese company doing mostly action activity recognition. So I did have a little bit of experience with this kind of stuff before diving into this big project. So I'd like visually inspect the actual source material of this project. And the most important thing to measure, I mean, you can measure a ton of things in boxing, right? The ring position of the fighters, like how they move, are they southpaw, or they orthodox, so many things. But really the thing that is the most important thing to measure is like, are they landing shots or are they not landing? And more importantly, like the shots they're landing, what kind of quality of? Are they landing hard? Are they landing accurately? Or are they like partially defended in some sense? I guess you might already like have a look at these images out there. There's a little sequence of the eclipse of 4 punches in the frame immediately preceding it and following it. And so if you look at this, I imagine you might find it difficult to see which would be considered landed and which would be considered not landed off of this footage here. It looks pretty much the same, right? But they are not. 2 of these are landed and 2 of those are not, as annotated by our professional boxing annotators. Originally, I was thinking, my first thought was, okay, we got to go with, pose estimators, key points, something like that. That's like the bread and butter of action activity recognition, typically. But in my experience, I figured maybe not actually, because with these annotators that I was able to hire, when they annotate what land and what not land in slow motion video, their annotations correlate quite well with one another. So clearly they sort of agree what's landing and what's not landing and what the qualities are. Yet somehow it's not really clear why. Like, it's very subjective in some sense, but still they matched. Things were correlating. They couldn't really tell like why a specific punch, why was this landed in these blurry circumstances, why wasn't this? Sometimes, oh, it was maybe like a glove that slightly deflected. You have an odd change of angle to the head. In general, what tells you what landed, what didn't land, are small details. Of course, you have these big punches that are beautiful and everybody can see this is a landed shot, but that's not really how it works in boxing. You typically have between 100 and 200 landed shots, and most of them are like low to mid impact. So you sort of wear your opponent down with all these. So these are really important to detect. And so if you can only really detect the big bombs everybody can see, that's not really sufficient. So I ended up deciding to not go with pose estimators or key points to try and figure out how to do this. Just because I figured if I do that, I'm going to filter away a lot of information that is clearly very relevant to determine whether or not a shot landed. So, oh, and here's another example. This is 50 FPS. The other one was 30 FPS, typical 1080p frame. Even with 50 FPS, you tend to have the same issue. So the approach I went with was with a direct approach and made my own models. And so what I mean with direct approach is like a video approach. So there's no intermediate stage of key points or poses or whatnot. Just like a virtual cameraman following the fighters around and telling me what they do. And this also means we had to create some really gigantic data sets. Probably that's one of the biggest challenges actually of building this. I think I've spent more time with the data than I even spent building all these fancy new models for Deep Strike, as we call it. Our detector data set is of similar size as MS Coco, and it's actually substantially smaller than our accident classification set is now. So after about a year and a half of just me being solo and, well, with 2 annotators I could afford to hire, and coding up and trying different things, we had something that started to look pretty good. And so we published a tech demo. And this web just blew up. It went viral. So we published it on LinkedIn, where it just blew up right away. We also published it on Reddit, where it did too. We published it off of Twitter and Instagram and YouTube. I'd made accounts for us, but since we had 0 followers, it didn't actually go viral there because there's nobody really to like it and share it. But other people fortunately shared our video on there, so we got a lot of attention here. One little tip, if you guys are doing something similar at some point, make sure your logo is easier to see than the logo I put here, because we made this tiny logo, and it became almost invisible for the eye. Let me just show you this tech demo in case you haven't seen it. Yeah, so this is what it looks like. And so I was quite deliberate at making it in a way that it should be easy to understand for everybody what's going on here. Yeah. And so it runs for professional boxing. You should see here classical fights as well, like black and white. Works as sparring. I tried from the beginning to make it as generic as possible with the way I was curating the data sets. So let me. Yeah, but so here came the challenges. At this point, when this video went viral, I started expanding the team a little bit because like a lot of people were reaching out and said, this is really cool, can I be a part of it? And so the team was expanded a little bit, and so now we're 6 people. But the first challenge is that video you saw there was let's say like a highlight of the highlights, because it was, you have a 12 rounds of a fight, and most of the time you have errors. So, go and pick out where you have the best results. And we had okay learning curves for the models, for the action recognition models. But I mean, they looked nice, but the slope wasn't too nice. You needed extreme amounts of data here. So that was one of the issues we faced. Another issue we faced where we were running out of money at that point. So the little money I had raised initially was just disappearing, and so we needed to raise more money. Now this happened then, I guess, about 4, 5, 6 months ago. So Q1 2023. I don't know if any of you guys tried to raise money during that period. So it was bad timing to start raising money. I think I saw some numbers that said the market for raising money was only 7%. So startups in the US had only raised 7% of the money in Q1 2023 that had in 2022 and 2021. So it was a tough market. But fortunately, we were able to raise a little bit of money so we could keep going, probably because of all that positive attention that we got to our tech demos. And so again, we could expand the team a little bit, hire some extra data annotators, because a little note here, doing this kind of annotation work here actually requires a lot of knowledge. At the very beginning of the project, I tried to use annotators. You can get those online. That sort of helps you. The part-timers in some sense was not a good idea. You really, for this kind of work here, we needed people who were specialized in boxing. So now, 6 months later, things are looking better, and we can actually run the whole thing for entire fights while still looking good. So let me try and show you another little. This isn't, well, I guess this isn't really a demo now. This is actually something we're publishing and getting out there. So I have to unfortunately close and open this because this PDF presentation was made on Ubuntu and it doesn't work well with Windows apparently. But here it is. Here's our. Okay, and so going back now a little bit to all the things that we measure, I decided to pick up this Ivan Rekak and Devon Alexander fight that started it all in some sense. I had actually almost forgotten about this fight, but then Saturday, as I was getting ready to get on the flight and was preparing some slides, I was like, oh, we should run through this fight, to actually see. Can it then predict what the commentators couldn't predict and what the CompuBox guys with their clickers couldn't see? And it kind of looks like it does a pretty good job at that. You see how Ivan Rekak, both in terms of high impact shots and in terms of landing shots, actually are outlanding the other good guy by a fair bit, clearly winning the fight. So at least to deep strike, this knockout that came in round 6 was not as much of a surprise. We actually measure many things here. We also measure things we call pressure and aggression, and we take all of these shots being measured and group them into combinations and exchanges. So we create these Sankey diagrams off of it. Measure footwork and distance and balance, various things. Pressure and aggression were maybe the most interesting things here to note. Because what is pressure? Like what does this really actually mean in this context and aggression? And those are two words that are just so often used by commentators and people in the sport, yet nobody really knows what is it, like what is our definition. It's used sometimes almost interchangeably. So we decided in order to get a metric for this, we'd have pressure and aggression be like compound metrics. So these are metrics, we're actually measuring other things, and then we say this is a sign of aggression, this is a sign of pressure. And so for pressure, we say, well, if you are making your opponent move backwards and you yourself are moving forwards, that's an indicator of pressure, of applying pressure. If you got your opponent on the ropes or in the corner, that's another indicator of pressure. You're staying at the mid-range or inside, again, another pressure indicator. Same for aggression, but different indicators. So, are you throwing combinations? That's an aggression indicator. Or are you initiating or ending exchanges? That's an aggression indicator. Or throwing punches with high power commit, that's another aggression indicator. And so then we just say, okay, well, what percentage of a round has the fighter shown or triggered one or more of these indicators? And that's then our aggression metric and our pressure metric. Yeah. So we've been getting a lot of reactions in the sport from what we're building here. We've been getting amazingly positive response from boxing fans around the world. That's been the best thing. It's almost too much. Like, I try to answer all emails, but it's we're almost spending too much time on it, like answering all this like fan mail and people who are excited about what we're building. We also talk with most broadcasters out there in boxing, at least the European ones. Only one of the American ones. Maybe they have a different perspective on transparency. I don't know. And also we're working with quite a few performance analysts out there, including Team USA, some big gyms around there. Actually working with even a gym here in Vancouver called Quinn Boxing. So commissions though, governing boards in the sport, promoters, how much have we heard from them? Zero, absolutely nothing. And they've absolutely heard of us. There's no question, because pretty much everybody involved in the sport have heard of us by now. So why is this? We're actually not too surprised about it, because we have a lot of good data about different fights now, and we can see a lot of shady patterns, let's put it that way. Boxing, I suppose, is called prize fighting for a reason. So if any of you guys follow boxing, you might have heard about the Haney Loma fight controversy like 2 or 3 weeks ago. At least in the boxing circles, that's one of those fights where everybody gets really upset and angry and say, oh, I don't want to watch the sport anymore, and so on. That controversy, we saw it coming a mile away. It was so clear from the previous data. So Lomachenko, for a couple of his previous fights, we'd run him through, and we could see in his previous fights that the scoring of the judges was heavily skewed to his disadvantage. Not only that, the guys with the clickers apparently also, for whatever reason, were skewed to the disadvantage of Loma, which is quite interesting, because those numbers that are put on from the guys with the clickers, they actually have a huge impact on how the viewers perceive what's happening in the fight, because it's so fast. As long as it's reasonably close, most viewers actually have no idea. Yeah. But we saw that coming, and it's not the only time we see that. We see that quite a lot, actually, with various patterns. And why does this happen? Well, it's really about money, right? It's about revenue. And so to us, it seems pretty obvious, because the pattern repeats itself, that it's really about if you have one fighter who can sell a lot of tickets, you have another fighter who maybe cannot sell so many tickets. It just makes sense for the entire establishment that the guy who sells a lot of tickets, he's going to get the decision. And so we see how sort of the whole industry conspires almost naturally to make sure that happens. Yeah, I think they just see it as they're putting on the circus that people want to pay for. What happens in the ring, that's like real, that's fighting. But what happens outside of the ring, that's where the circus sort of enters the game. Yeah, so we're working with broadcasters. They seem very interested in this, because they don't want to get left behind. What if one of their competitors starts showing all these cool stats, and then what happens with them? And so a lot of the broadcasters are sort of on us, but we expect to see some resistance from promoters and commissions, because it's really quite a lot of money that makes sense. Like Loma here, imagine you have this guy fighter who's great at fighting, but he's from somewhere in Central Asia. He barely speaks English, with a name nobody can pronounce. He's just going to sell 10% of the tickets that the other, young American social media superstar is going to be able to sell. And so I guess that's just how it goes in that sport. So we are expecting some resistance from promoters and commissions, because what we built here is probably not too good for their business model. So what are we going to do about that? We decided we're just going to make stats and content for everybody in the sport. So, make a platform, which we're doing right now, where anybody can take their videos and they can upload them to it, and then get stats for it, and get automated highlights and all this kind of cool stuff. And the thinking is nobody can prevent us from doing that. No commissions or anything like that. So also another reason is just that in most sports now, there are plenty of tools available to do similar things, automated stats and content, except combat sports. But they're really left, the poor guys are left without anything there. So that's the direction we're moving in, and we want to change that. We want to make sure that everybody can get automated punch stats and content generation in combat sports for the long tail. So that is not to say that we're not willing to work with broadcasters or any commissions that want transparency. It is just to say that we don't actually expect any of the commissions to really want transparency. They want to be in control. So something cool we can do with Deep Strike is we can do auto production. And so with auto production, what I mean is Deep Strike was created originally, built in such a way that it would be generic, right? You can apply it to some what's called a dirty feed, where the angle changes, does automatic re-identification. All these things happen automatically. So it was actually quite easy to build an extension to DeepStrike where we create virtual cameramans, some logic to switch between the different cameras, some OLED graphics that can be added, some highlights that are then added during the round breaks. This was actually pretty easy from what DeepStrike could already do. So that's something we can do now here. And I got another little demo for you. If I can figure out this window system. Yeah. So this is just sort of to demonstrate what we can do now. And we can do this right now in post-production, which means like, give us 1, 2, 3, however many videos you got. And you could place them wherever you want, pretty much, as long as the whole ring is visible. So something like this here, you got the first one, cam 0 is placed like a typical main camera. And then you have these other cameras with the virtual cameraman. And what DeepStrike does is to zoom in on the fighters, track them as they move around, add some overlay graphics, some punch stats, switched angle. You maybe noticed there how I was refereeing that fight. I was stepping in front of the camera, and so DeepStrike shifted to another angle. Then during the round breaks, it's going to add some cool overlay graphics and a little bit of stats about the fights. And also some cool highlights, because again, picking highlights is pretty easy when you know when the cool shots are landing. Because typically in the highlights between round breaks, what you want to see is the big bombs landing. Yeah, so that looks something like that. The highlights, and then it'll switch back to the match when it gets back on. So, oh, but actually I got another video here I can show you. So we've been using testing this now in practice, the auto production here at some events, and it works pretty much like we want. So this was a fight in Shenzhen, a fight night, where we were asked if we could go because some people had seen the content we were creating, and they were like, "Can you go and do it for us?" So we figured it was a nice way to see if people actually want to pay for the content, and which they did. So that was nice. Making me shift forward. So then as the fight begins, you will see that the camera starts zooming in and shifting and the kind of stuff that's happening before. Should be starting soon. Yeah, and so there you kind of got the effect. And so it's like tracking the fighter, zooming in, adding some overlay graphics, it starts counting what's happening in the fight. Yeah, and all of this is where the old version of DeepStrike, but it's like fully automatic. So no human supervision on this here. Oops. Okay, but back to the PDF. Okay, so second session of challenges here. Right now, we can do it as post-production only. So, which means people will have to record their fights and upload them to like our website in order to get this kind of content. We do all sorts of highlights as well, but yeah, they gotta do it after the actual fight. I feel the audio is still on somehow here. Oh yes, there you go. Yeah. And another challenge is timestamping and anchors. So we manually set, at least for those samples there, we manually set, okay, here the round starts, here the round ends. This guy is blue corner, this guy's red corner. The anchors we've actually fixed now, it works pretty well. The timestamps, we've got like sort of a semi-okay solution that works okay. So we can add more beta testers to our website, but it's not perfect by any means yet. That's something we'll have to look at in the future. Boxing is very messy, right? You know, a lot of things can happen. You know, in one fight, you might have a guy who's pants are falling down, and so they gotta take him to the corner and then put them up, tape them up, and a lot of weird things can happen during a fight. There's a long history of weird things happening in fights. So yeah, that's going to be a little bit of a tricky thing. It works okay now as long as everything is pretty much standard. Then it's going to set the timestamps automatically now. But we need to work a bit more in the future because weirdness is just part of boxing. Also understanding ref calls. So if a guy is on the floor, that could have been because of a slip or because of a knockdown. It makes a huge difference in terms of the scoring and recording what's happening. So we actually need to start doing some classification of the ref signals as well in order to do this automatically. Also highlight quality. So the way we generate highlight now for our beta users is that we just take whatever the biggest landing shots and we make like a little video of that with the virtual cameraman. However, high quality highlights, it's also about other aspects of the fight, like beautiful defensive moves, defensive techniques that are uncommon but very cool, that kind of stuff. And so we don't measure guards or defense yet. In order to make automated highlights that are quality comparable to what humans can do, we will probably need to measure more aspects of the fights, like especially guards and defensive techniques as they happen. And then there's also the recording quality that people can do with their own smartphones. Most smartphones now actually have the capacity to record 4K 60 FPS, which is great quality, and we can get some very cool content out of that. The problem is most phones also overheat after about 5 minutes of doing that. So yeah, that's a little bit of an issue. And also just the general difficulty of recording with multiple cams. So a lot of fighters, what they will do at fights, now we're not talking the big leagues, we're just talking like fights at the amateurs and so on. They'll have their friends put a camera on a tripod, or they will have they will do it themselves. Rarely will they put up multiple cameras, because then you have to like go to the other side and press start and stop, and so that's a little bit of a difficulty of using this. So where we're heading is we want to create a live solution. So right now there's these very popular products out there, like the VideoCam that came a few years ago. There's something called Pixelot now as well, Pixelot Air. There's the Huddle Focus, I believe it's called. These products that people can bring to like a soccer game or a basketball game. I think most of you probably heard about them. They're very cheap and affordable, easy to use, and then you can get some cool footage of what you're doing. None of these solutions are good for combat sports. They're based off of a model where you have 2 ultra-wide angle lenses in this one box, and that records the entire thing, and then you crops it and do some analytics. In combat sports, you don't have a gigantic field, you have a tiny field, but it's really important you see it from multiple angles because of occlusion. And so what we want to do, ideally, what we're doing is we want to do that kind of product, but we can do it for combat sports. Yeah, something easy, simple, plug and play. And we feel there's a lot of perspective to this, because if people got that in the gyms, they can share their sparring, they can stream their fights, they can use it for the locally organized tournaments. And one can put some structure to this very, 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 very messy scene of combat sports at the amateur levels, where nobody really knows. Like there's not a ranking system similar to other sports, because it's just all very messy. And so we figured if everybody uses our little Jabber cam to record their fights, Deep Strike could just rank all the fighters. So you can see where you ranked globally, locally, continentally, even down to your own city and your own weight class. And a lot of other cool things you can do with this type of product. And yeah, so we're actually hiring. So we managed to, despite all the troubles of raising money at the worst time to raise money in 15 years, we were very fortunate to actually still get some money. We had to reduce our expectations a little bit. People were telling us after our tech demos went viral, you need to raise billions and billions now, and we had to reduce our expectations a little bit for that. But we managed to raise a very nice round, with 2 of the participants being brand name investors from Denmark that have a special status there. So we also got equity-free funding from a Danish growth fund. So we're looking to hire a little bit over the next 3 to 6 months, specifically. Also, that's why I'm here. We want to hire some AI guys at some point. Ideally, a guy who can initially work with me, but then over time take over and become the head of AI for what we're building here. Because right now I'm wearing 2 hats in the company, and that's a little bit too much, I think, as we move ahead. Yeah. Okay, so that was my talk. Thank you so much for listening.
Fantastic talk, thank you. From the data that you collect, you mentioned that you both have a detection data set and an action classification data set. From the detectors, it looked like heads and hands and body. That's what you're detecting in the videos?
Yeah, and a few more things that weren't shown. Yeah.
Okay. And then for the action classifications, you didn't really mention what
yeah, that was actually, yeah, that was quite specific, because we spent quite a bit of time figuring out how to do this in a way that we can run it real time without a lot of computational effort. So it runs, actually the action recognition, it's video classification, but it runs as fast as image classification. And so there's various tricks there that we were told, you know, to not put in, because some of it was patentable, apparently, we've been told. So yeah, it's not something we can share at this current moment, but it's video classification, yes. Sure. Yeah.
Thank you. Really impressive work. I'm wondering if you've heard from athletes themselves that want to use this for training, and if you've considered, if this is widely deployed, how it might change the way these fights look and the way the athletes actually behave.
Oh, we've got a lot of people getting in touch with us. Yeah, we have a wait list. So right now there's only 5 beta testers. So we've been very selective with who can get on, because otherwise we'll be spending all our time manually setting those timestamps for all the videos they upload. So we have a wait list of about 700 gyms who want to get involved and use it for training and also for analyzing the fights after them. In terms of how it can change the sport, I think actually it can make, maybe for the first time, analytics become something that is generally used in combat sports. So up until now, only the biggest teams with the biggest budgets have a little bit of analytics, because you can imagine like manually annotating all this data from a single fight in boxing is extremely time consuming. It's like 40 hours of work for one fight. And so unless you're like really rich, like you cannot really afford that. And since there's just not that much raw data to work off of to begin with, this is in some sense unexplored. What's going to happen in boxing now that instead of just the 10 richest clubs can afford to get some data on their fights, now suddenly everybody can afford it. Like what's this going to do to the field? And we don't actually really know yet. We'll see. Yeah.
Yeah, really impressive products. Congratulations. I just had a question about when you're building your initial data sets, where did you get your videos?
We just scraped the internet. I hope we didn't do anything illegal. Yeah, we got about 16,000 boxing fights that were all just scraped from the internet.
Okay. And have you since incorporated like AI models into your annotation process? Or
Yeah. So what we can do now is we can run Deep Strike, and then we take the output off of Deep Strike, and then the annotators get that, and then they just correct what Deep Strike makes. Yeah. No, that is heuristics. So that heuristics are all just working out of the output of Deep Strike. So Deep Strike logs all the different things that are being logged, and then we have something afterwards, the post-production thing, and that's all just heuristics based off of what comes out of a Deep Strike. It seems to be working okay, but I think especially for the whole setting of timestamps, we might want to make specific research and models to figure something better out there. Yeah. Yep, so it runs independently as it is now. If there's multiple cameras, it runs independently of each of them. And then the output is also merged into post-production. But we're working on setting it up so we can merge it as it's running for the broadcasters.
Yeah, one more question back there? Yeah. So the premise of the entire thing was that you found curious how matches were.
Yeah.
And also what was
compared to CompuBox?
Yeah.
Well, the main difference is the annotators. They can actually watch the punch happen in slow motion, right? And step through frame by frame, watching as many times as they like. Whereas the CompuBox guys, they get like, 200 milliseconds and then they have to press the button. And I suppose that's really the main difference there. And then Deep Strike just learns to mimic what the annotators do. The annotators, the correlation between the annotators is pretty good, but there is some subjectivity there. So one annotator might say, oh, this is a category 5 punch. And then this annotator says it's a category 4. So they're not always in complete agreement. But the models seem to learn that quite well and still give some reasonable approximations, for what an annotator would say.
We have a question on Zoom. Can you get to that?
This is a Windows machine out of my element. Yes. Oh, yes. Yeah. Okay, so the question is, does your system need any calibration now or in the future when you go live, and do the fighters get detected automatically? And so the answer is yes, the fighters do get detected automatically. So Deep Strike just, as soon as it sees 2 fighters and it's sufficiently confident that the fight is ongoing, it just assigns a corner and an anchor to each of them. And there's no fancy way of assigning a color right now. It just goes by the coloring in the image. So if it's an amateur fight where they have the sort of designated blue-red clothing, it usually does it correctly. So blue goes to blue and red goes to red. For a professional fight, we have a little interface so that the guy controlling the system can like manually switch it, because it's going to be basically random whether or not Deep Strike chooses the right red corner here and blue corner there, because there's no coloring happening in there. Yeah. So yes, it does get detected automatically and assigned. Yeah.
One last.
I'm interested from like a competition point of view. Do you foresee that fighters would lose a fight based on bias?
Yeah.
Could potentially come and use this as like scientifically backed evidence to prove that they actually won fight?
Probably.
That
Yeah.
being kind of the flipping point where governing bodies would have to get on board.
Mhm.
They're then having arbitration for sport cases where there's evidence they won the fight.
Yeah.
Anything in that direction?
A lot of people are doing that, and so we uploaded one of those YouTube videos for the Loma Haney fight, and then you have all the people commenting, oh, these people should be arrested, and this kind of stuff, and people are really upset, and the fighters, I think so too. What's actually going to happen? I don't know. I think a lot of fighters will, when we open it for everybody, they'll just run their own fight through. If they're unhappy about a fight they felt they should have won, to see if there's statistical evidence that that's really the case. I think the commissions and broadcasters, not the broadcasters, the commissions and the promoters right now are definitely thinking, okay, what do we do about this? Because their entire business model is about building up fighters to make them look like unbeatable heroes. But often during that path of building up your unbeatable hero, he meets one journeyman or two and has an off night, and he probably should have lost that fight. And so Deep Strike is brutally honest, right? It's not going to give you any credit for being good at selling tickets. And so for their thinking, this is probably not too great. I think what we're going to see in the future might be a lot of like fake AIs. And so what I mean by that is I see the Professional Fighters League have an AI thing, an AI scoring that nobody knows where it came from, and there's no tech demos and nothing. It's just this percentage thing. Because they really have a very strong interest in making sure that the viewers continue to stay fans of the guy who just can sell a lot of tickets. A lot of people were upset that Loma didn't get the decision against Loma Haney, but if they want to support their fighter, they need to start paying, buying tickets, because then they're going to let him win. Yeah.
Okay, I think we should thank the speaker for a very informative and entertaining talk.
Thank you. Thanks. I will be around, yes. So,
Okay,
yeah.
those are your questions.
All right. Thanks.
Okay. Done? Next. Our next speaker is Yang Liu from Magic Leap, who's going to talk about a scale invariant trajectory simplification method for efficient data collection and videos.
I'm just gonna find that one.
Scale invariant sounds like stiff.
Kind of.
Good.
Yeah. By the way, I'm really glad that I'm after the last speaker, Alan, and I think the people already grab a lot of attention for how challenging that the data collection is really hard in the video. So this work is actually trying to solve this problem efficiently. Yeah. Okay, thank you. Thank you so much. So, hi, I'm Yang, and today I'd like to present this work, a scale invariant trajectory simplification method for efficient data collection in videos. And this is a joint work from me and Louis from Ubisoft. As I just said, this task is actually we want to speed up the semi-automatic data collection pipelines for object detection and tracking in the videos. And what we are doing is that we propose a new trajectory simplification method actually to trying to compress the existing tracking output, and then we can just verify and review a small portion of the output and get really high quality ground truth for the trackers. And our method is also able to compress the video trajectories if you want. And our code base is available in the GitHub. And this is the QR code for the code. And our code is actually can be accepted the normal tracking output like the MOT tracking output and directly export to some like fields which is directly can be input to some CVAT video annotation tools. So if you want, you can take a try for it. Let's go into the detail. As we just noticed that actually the object detection and tracking is kind of the crucial for the video sport analysis, especially, for example, we want to do the detection and tracking and want to do the analysis on the top of it, or we want to get the highlights or action detection. Maybe we also need some bounding boxes or tracking trajectories for it. However, as we know, like getting the training data is pretty expensive, especially you want to annotate a whole video, as Alan said, that maybe we need to take about 40 hours to get it. And also, if you want to run into some new sport like the compact boxing or volleyball or some other stuff, which nearly do not have some great like tracking data set like Soccer Night, then maybe you need to start it from scratch. So that will be pretty costly. I really like a practical way we can do that is actually we can using some pre-trained models and some detectors and trackers to get the tracking output. And then we can just manually fix the tracking output like by every frames. But it's still pretty expensive, we can see. And it also like takes a lot of efforts. So in this case, it's a really naive solution is that we can just do not do the annotation for every frames. We're just using the uniform sampling to sample some frames to do that. As we saw it here, like if we can get the original output in the bottom figure, and then we can just sample a few frames and then verify and correct the tracking output for those frames. And then we can, based on, for example, retracking or based on some like interpolation, we can recover the actually high quality ground truth data. However, that is definitely doable, but it's not optimal, which means that so for some, especially for sport, like sometimes we have the dynamic change and sometimes we also have some motion blurs. And in this case, some frames is definitely more important than the other frames in the trajectory. So in this case, what we want to do actually in here is that we want to improve the selection part, which means that actually we want to find the most important key frames in the trajectory. And then we can just modify them and get the high quality ground truth. And in this case, we can kind of treat this problem or transfer this problem to trajectory simplification, which means that we compress the current trajectory into some like by just selecting the keyframes inside of it. But however, if we just simply applying the trajectory simplification method, there are some limitations. Like the original trajectory simplification method is mainly designed for the GPS data or post trajectories. And actually it's not optimized for the bounding boxes and or other like visual trajectories. And also it cannot handled by the noisy trajectories. So in this cases, we want to solve these two things in our proposed method. Our methodology is mainly like these ones. something in the right figure, and you can see what we got is that we got the tracking output as the input for our algorithms, and then we kind of start initial searching space, which actually remove the noisy observations in the original tracking output, and then we start to optimize our trajectories and find the most important keyframes in those trajectories. As final, we only need to verify those important keyframes in here. As example, we only need to crack the B2, and finally we can, based on some retracking or based on some interpolation, to get the final ground truth output or ground truth trajectory. So let's go into slightly detail in here. The first step is actually we cause the initial searching space. And what we are doing at here is that we want to remove the noisy observations. We'll keep the most important and necessary ones. When we say the necessary bounding boxes, we are referred to two parts. One is the high quality bounding boxes, which means that actually the detection and the tracker is really confident this bounding boxes is correct. And the second part is the outliers, which means that actually this situation, we want to cover something like irregular appearance. Like some people is just falling down and it's never been happened in the previous training set. Or then in this case, it's something that we need to consider as well. And what we do in this step is something shown in the bottom figure at here. Basically, this is an example of a trajectory from B1 to B6. And in here, we have three high confidence bounding boxes, which is B1, B4, B6, and it is marked as green. And we will do the interpolation between those ones and get the interpolated bounding boxes. And then we will calculate the error matrix between the interpolated bounding boxes and the low observations, which is marked as blue. And the final result, if the error matrix is higher than a threshold, we think this is an outlier, and then we will be recursively do those steps until all the outliers is found. And in this cases, in here we will be only select add the B2 into the searching space, and then we will start the optimization. But in this cases, from this step, actually we can kind of solving our first issue, which is how to get kind of clean the trajectories for the following up optimization. But there's still another issue, which means that the previous trajectory is actually designed for the point-based. The way to solve it is actually we are actually using some scale invariant metrics like the IOU, DIOU, or something in here is actually the weighted IOU. And then we will to replace it from the other synchronized Euclidean distance, which is proposed by the other trajectory simplification method. And in this cases, we can also kind of solving the problem for the bounding box trajectories. Then we can go to the next step. For the next step, we just want to simplify our trajectories, or what we want to do at here is actually we want to reduce the number of bounding boxes. We'll minimize the whole trajectory integral errors. And what we do is that actually we're using a DAG to establish a graph for the whole trajectories, or actually for the all potential simplified trajectories. And the final simplified trajectories is the unique path from the last bounding boxes in the trajectory to the first one. And in here, it will be B9 to B0. And in this example at here, the final simplified trajectory will be B0, B5, and B9. That's in this case, it's for these 10 bounding boxes, we only need to verify and maybe crack these 3 bounding boxes. Those is the general overview for our method. Sorry, I can go into the detail. I cannot go into the detail because of time limit, but I will go with the evaluation here. Since actually we are the first paper to solving this problem, so we just need to want to propose a pipeline to simulate the real trajectory correction to make it more cost efficient. And what we do at here is that we get the input trajectories from the pre-trained detection and trackers, and then we select the keyframe based on any method like uniform sampling or other trajectory simplification method. And what we want to simulate at here is that when we got this simplified trajectories, we just simply crack those one based on the ground truth trajectories. And in these cases, we can get get the clean, simplified trajectories, like the human annotation. And then we just recover the full trajectories based on the interpretation, and then we like evaluate it through the ground truth trajectories. The evaluation, in order to come to the fair comparison, actually we evaluate our method in 3 data sets, which is MOT20, the soccer night, and the dance track. And also to do the fair comparison, we comparing our method with the uniform sampling, the TDTR, which is a DP-based trajectory simplification method, and the MRPA, which is a DAG-based trajectory simplification method. And in here, you can see our method is performance better if we check about the red line in the top, and yes, it's red line. And actually, it's performance better in all compression ratios, in all performance on bar, in all compression ratios, in all data sets. And if we check about the table in the bottom, actually, we can see that in the all detection and tracking method, our performance is better. And especially since we are optimized for the IOU or the IOU scores, the detection metrics will be even much more better than the tracking metrics. And also, there are two interesting things we want to find out here. Is that one thing is that actually the classic point-based trajectory simplification method, like the TDTR or the MRPA, actually performance similar or performance slightly worse comparing with uniform sampling, which is kind of surprised me at the beginning. But if you can check about it, you can see like, especially for the detection metrics, like the IOU scores or IOU means, you can find actually performance worse nearly in all data sets. Which means that if we want to using those like trajectory simplification to compress the visual trajectories, we need to do some modifications. That's why we need to propose this method. And the other thing is that actually, if we want to really got high quality ground truth, especially for some complex trajectories, sometimes we need to reduce the compression ratio. For example, the dance tracker needs, for example, slightly lower compression ratio to get like 95 or 90 HTOA scores. Sorry about that. A quick analysis about our model is that actually shown in this table. Two quick takeaways that first, the IOU or DIOU method, like error matrix, which is the scale invariant error matrix, is actually the most bonus we can get from the thing at here. Like it will give us the most performance improvement at here. And the second thing is that actually the outlier is also important, especially when we check about the IOU mean scores. It can be, if we without the outliers, the performance will have a significant drop. Another, I'm not so sure whether I have the time for it, but another like analysis at here is actually for the trajectory noisy impact analysis. And in here, like we just simulate our noise trajectory noises for the detection noises and ID switches noises. And in here, maybe a really quick takeaway is that the trajectory completement is kind of crucial for grabbing the high quality ones. If we check about the soccer night, we can see that actually the performance is much better comparing with the real data, because the raw pre-trained model cannot get, we are missing a lot of like segments. And in these cases, if we want to get high quality data, it will be really helpful if you can get a complete trajectory based on maybe generated, guided by some other sensors. And that's all I want to share for today. And I will take the questions now. And this is a demo video we have. Any questions? Go ahead.
Yeah, I have a question. Like the way you sample keyboards, you do keyframes, you're kind of like sampling one distribution of potential motion that you have in the frames. Are you make force diversity? You might have some cases where you have very low motion versus very high motion. You have some regularize somehow and force and keep the diversity of motion.
Yes, that's actually a great question. Actually, we do that like check based on our metrics, and we also have another proposed method called the general integral errors. And in these cases, we can kind of handle those stuff, but limited to the time, we cannot present for here. Yeah, if you want, you can check the paper for the stuff. Yeah, yeah, thank you.
Okay, thank you.
Thank you so much. Yeah.
Is Naga? Okay, the next talk will be by Naga Rakata. I hope I pronounced that properly. An oral presentation on Spartan, a self-supervised spatial temporary transformers method approach to group activity recognition. There we go. Thank you.
All right. Hello, everyone. I'm Ravi, a PhD student from University of Arkansas, Fayetteville, and I'm here to present my work on Spartan. This is a self-supervised spatiotemporal transformers approach for group action recognition. And I would like to thank NSF and DART for supporting the project. And going into the presentation, starting with the motivation of the problem, I consider the basketball video of a 3-point success as the input video, and then we sample the video into like multiple frames at a defined sample rate. And then for the representation purpose, I consider the first and the last frame in the entire sequence. So initially, I prefer to compare with the previous method and why my method is like much better than the previous one. So the previous method, if we see, it gives a lot of irrelevant like attention to the actors outside the field, as you see in the red color. And the green people are the most relevant actors, which led to the proper group activity recognition. And because of more irrelevancy, so it gives a wrong prediction as a 2-point success. Coming to our method, if we see, there's a lot of relevant actors which are given attention along with the positions of the ball and the position of the actors in the scene. So thereby we see a better prediction with good prediction, confidence scores. And now the comparison with multiple previous works. So in this work, we consider actors and the ball and their position as the main factors to perform a better recognition. And then during the pre-training step, so the feature extraction and relation analysis are the two main things. And the first thing is SAM, which came out in 2020. They use a pre-trained detector and graph convolution network to do the relational analysis, which gives which gives more attention only to the actors leaving the ball and position unattended, because we know detectors, they have due to occlusion, they cannot detect the others. And the next method is DFWSGAR. They use a motion module which compares the frames, only the adjacent frames, so they miss the position of the actors. And coming to our method, we are using cross-view correspondences with a width backbone. And then we perform knowledge distillation using video transformers. So thereby we have all the information required. The contributions of the work goes as initially the cross-view correspondences, where we vary the sampling rates of the input video. And then we feed the global temporal views to the teacher network and the spatio-temporal views to the student network. And then we do the knowledge distillation, so to analyze the relationship across the global temporal and then the local temporal views, we use inter-teacher and inter-student loss. And similarly, we have an inter-teacher and intra-student loss, where it is global global temporal to local spatial views. Now, seeing at the method, that we developed for the pre-training. So similarly, we did for the like as we see in the motivation. So we have an input video, and then so first we sample the local spatial temporal views. Initially, it is the local temporal view at a defined sample rate, and then we sample the same thing spatially. Followed by we have the global temporal views, which is upsampled from the local view that we have. And the local views are fed into a student video transformer, which yields the corresponding feature vectors as the outputs. Similarly, followed by the global temporal views are fed to the teacher network, and we perform the knowledge distillation using EMA. And we have the corresponding global feature vector and loss functions. So the proposed objective functions are calculated as below. So we first calculate the normalized feature vector using this. And then to control the sharpness of the exponential function presented, we have tau in the equation. Then we calculate the inter-teacher, inter-student loss as below, and then followed similarly we calculate the inter-teacher, intra-student loss, where you see the Q is we sum it over the Q number of patches that we sample in the local spatial view. Finally, the overall loss is the combination of both the above losses. Now, coming to the ablation study, like we analyze how each component is performing related to the view correspondences. So first, we consider only from the local temporal to the global temporal view, we see somewhat like a poor performance. And we consider the other way, like from the spatial, local spatial to the global temporal, still a bit better, but we consider it as bad performance. And then we do the other way around, like instead of considering the global temporal view, we consider the local temporal view. Finally, we see a better result when we do from the local to the global views. And the next ablation experiments are between spatial and the temporal variations. If we consider only the spatial views alone, we see the performance is like so bad. And then if we consider only the temporal views, it's quite better than the spatial alone, but still it's not significant. So we have both the spatial and temporal views to show better results. And then comparisons with the state-of-the-art methods, as we perform the experiments on the volleyball and NBA dataset. Initially, the volleyball dataset, we consider the fully supervised setting, and then the weekly supervised setting. Our method is currently at the state-of-the-art results. And coming to the NBA dataset, we compare the group activity recognition models along with video backbones that are present, and we see our method like is proving some, like showing some significant results over there. Coming to the qualitative results of the ablation study, we present TSNE visualizations performed. So as we see in the base model, it's all clustered at the center, and then as we add more and more modules, the visual correspondences and then the motion correspondences, we see better clustering. And finally, the qualitative results. So we see the original sequence, and this is from the previous method, where you see the attention is towards the actors where they are moving. But if you see in our method, like it's mostly giving attention to the field and the position of the actors which are moving strictly. And then concluding the presentation, we introduce the first pre-training approach to group activity recognition by exploiting the spatial temporal correspondences, and we present a novel self-supervised learning strategy which jointly learns the inter and the intra-frame, that is the local and the spatial, forming the two losses which we introduced, and we achieved some good sort of results on both the volleyball and NBA data sets. Thank you for your time. Any questions? Any questions?
I've always been interested in pose as part of activity recognition. I notice you don't have anything that pulls out the pose. It's just position and
Yeah.
others.
Still considering the multimodality in this is still an open question yet. For now, we considered only the RGB, I mean the video data as the current modality, but in the future works, we are planning to consider the multimodality.
Your results are substantially better than the others. Have you thought about using it outside of sports? Is there some place where it would what's your thoughts on that?
Yes, so our main target, like why we decided to work on the group action, is we are working on a healthcare project where we want to understand the children's group action, like what they are doing. Since it is like very sensitive data, so we are not supposed to like publish. Yeah, so we decided to go with the sports and like test our methods or the hypothesis that we develop.
Sometimes the NBA is not very nice about letting you use their data.
Yeah. All right. Any other questions?
Any other questions? Okay, let's thank the speaker very much.
Thank you.
Lunchtime, I guess. Back here at 1:30. We'll see you at 1:30. Take some time and speakers or questions. Even if you're not in the context in which you usually see. Thanks. Yeah, going well. Yes, I am.